Okay, good morning. Is the audio good? Yeah. Good morning to the second day of the Quantum Autumn School 2023. We have several new guests, lecturers today, which will be introduced as we go. We start off with Mikael Johansson here from CEC in Finland.
Yes, great. So thanks, Tor, for the introduction, and it's nice to be here. And I think this sort of a combination of lectures and hands-on probably works very well. Now it got stuck somewhere. Okay, great. Yes, so my name is Mikael Johansson. I come from CSC in Finland, and I'll give a quick brief overview of how to integrate quantum computers with our and HPC systems and HPC systems in general, and also why we want to do it. But I'll just start with a quick introduction, and this you of course all know. What is a quantum computer? It's a device that directly exploits quantum mechanical phenomena to perform a calculation. And these phenomena are then superposition, entanglement, wave function phase, and so forth, as you very well know. But I just want to emphasize here that we really want to exploit these phenomena, while in classical computers, these phenomena are just a nuisance and you want to get rid of them. So that's one way to define it. But for the purpose of this talk, the more important definition is that what a quantum computer is not. A quantum computer is not a super fast version of a classical computer. That's the take-home message for this talk. So it is completely different, and in practice it means that it speeds up some type of calculations even humongously, but others not at all. It just makes actually the results worse and computation slower. And this is something that we need to keep in mind, that the quantum computers will not be a replacement of classical computers ever. And ever one shouldn't say, but not in the foreseeable future. So why are we then, as HPC centers, if we take this view, interested in quantum computing? And well, as mentioned, quantum computers will not replace supercomputers, but the two will merge. Because, well, quantum computers can do things that supercomputers are not very good at. Therefore, it's important to really stimulate this co-creation between the two communities. And I think also this autumn school is a very good example of getting people from different backgrounds together, and because there is plenty that we need to do together to really get this going. We cannot just develop quantum computers in a vacuum and continue developing classical supercomputers without really looking early on into what can we do with the help of quantum computers as well. And another reason why HPC centers are interested in this is that, well, we exist to serve our users, so we should provide the best infrastructure, computational infrastructure to our users. And the end users really need early access to an HPC plus QC platform, just so that they can start making the workflows quantum ready. So one needs to have something to actually run your ideas on, just so that you can prepare for when the quantum computers actually are sufficiently powerful to do something useful. And this is a really big challenge and requires lots of work, because now we are going to do a transition from classical computing to quantum computing, and as HPC centers we are very well aware of how difficult it has been to get users to transition from CPUs. Now the picture went away. But this will require lots of time to really get the transition going. And it doesn't only require time, it also requires really lots of resources and support from of different types. And here I think that the HPC centers really serve as a natural starting point for this transition, because we have in principle all the basic services in place, like user authentication and administration. That's something that we do all the time. Resource allocation and all of this, how to share a quantum computer among several users is there, and then of course all of the classical high performance computing infrastructure like storage and networks and classical computing resources. But we also have the end users. There is already a very large community that is interested in doing calculations that require humongous amounts of computational power. And they are of course usually interested in making their calculations even faster. Okay, and then a bit related to the afternoon already, where you will get to play around with a real quantum computer, is that what can you actually do with a small quantum computer that just has a limited amount of qubits? Well, quantum computers are very different from traditional computers. As we already mentioned, and there's a completely different programming style that you need to get used to, and they're also different from each other. So any program that you run on one quantum computer will give a different result if you run it on another. But also the same quantum computer will give different results when you run the same program twice, and it's supposed to do this. And this is a new sort of thinking that you really have to get through to the end user as well. And another thing that we really need to deal with for the moment is that quantum computers, they do compute wrong most of the time. And that's comes up a bit later in this talk, but and also later today. But it's something that we really have to live with. So all in all, this means that experienced HPC users really have to start thinking in a completely new way. So is a small quantum computer then sufficient to really bridge this gap between the end users and quantum computing? Well, not really. For the large majority of end users, it is very difficult to convince them why they should start using quantum computers at this stage. We have to provide the end user with some sort of prospect of quantum advantage, some reason why they should look into this. And if one is interested in just speeding up one's own research right now, quantum advantage is not obvious, as we know. So a question that one often gets is that why should we invest in quantum computing when it doesn't really give any immediate returns? Let's just wait, right? But then before we can answer this question, I think that we need to define what quantum advantage actually is. And there's actually several definitions for this, and one is this wall time quantum advantage, as I call it here. And the definition is just that, well, by using a quantum computer, you will solve some given problem faster than a classical binary HPC that can do on itself. And this is maybe the usual definition of quantum advantage, and we are still some time away from this. It really requires lots of development and progress, both on the hardware and the software side. But there's also another one that we can call green quantum advantage, that we can define that by using a quantum computer, we get a higher or more favorable solved problems per kilowatt or megawatt ratio. So this means that we don't necessarily need to solve anything faster with a quantum computer, but if we actually can solve a given problem using less energy, that's already beneficial for many cases. As long as you just get the answer, a reliable answer somehow, but it just uses a fraction of the energy, then this can be useful for many applications already. Just a note here that one always has to account for the total energy consumption and not just what it now took for the one circuit to run on a quantum computer, because there is, of course, all of the classical infrastructure around as well. Then there's a third one that one can call quantum quality advantage, and here we define that the quantum computer provides somehow a more accurate or otherwise better quality predictions. And this can arise from the fact that quantum computers need to solve some sort of a problem in a different manner. And then when you, in classical computing, do plenty of approximations, then you might get away with doing different sorts of approximations or skipping some approximations by using a quantum computer. And just because you do it, you solve a completely different, or at least largely different mathematical problem for a multidimensional optimization problem or whatever, then you can end up having a different solution that maybe is better. This could also happen already at moderate qubit count before you actually do something necessarily faster, but you just by doing it in a different way, you get different answers that then hopefully are better, and usually you can check this rather easily, hopefully, that you actually have a better solution. And then the fourth one, I call it quantum control advantage. And this comes from the fact that quantum computers are good not only at computing, they are actually, for the moment, they are much better at performing physical experiments. And that's because they really provide a highly controlled quantum lab where you can do experiments, because the qubits are quantum objects, quantum states, and the whole idea of a quantum computer is that you need to build up this experimental mechanism for really high precision control of your quantumness there. And this really can lead to the possibility of doing completely new types of physics or chemistry experiments. So not really using a quantum computer for computation, but just setting up some sort of a more or less weird basic research question on it and have it solved that way. And then there's, well, the last category, other. So, well, which just means that it provides some sort of other advantage to the users. And for academics, then, well, scientific publications and project funding is already a carrot. Of course, if everyone who is involved in academia knows that sometimes you just have to jump on the hype train to get funding. I'm not saying it's a good thing, but it's at least a carrot. But we have to take this seriously, because this is an advantage that if you are a scientist, then what you need is scientific publications, and even if quantum computing might not solve problems faster, at this point, then at least you can get nice Nature and Science papers out of it. For the industry, the carrots would be maybe mainly competence development, preparing for when the quantum computers are there, and also early IP creation. So on the algorithm side, for example, creating new sorts of algorithms before you have the hardware really can be an advantage, because then when the quantum computers come, then you can get income from just licensing your algorithms or other IP. And also for companies, of course, the public relations value cannot be underestimated. So by being involved in quantum computing, you give the image of being a high-tech, on the edge company, of course. Okay, here I put a timeline of when this comes, and what I want to point out here is that this quantum control advantage and the other quantum advantage is something that we already have now, so that we have quantum advantage right now. Then for the more computational results type of advantage, then we might have to wait some time, where I let everyone define what the unit of time here is, but let's not get into that discussion now. But the main point of this is that we actually have quantum advantage now, depending on how you define it. I just want to mention the non-computing applications here. That was the control advantage. So these are just some examples of what one has done with quantum computers that is not really computing stuff, but creating new physics on a QPU. And one, for example, use quantum computers to create these time crystals, where one has a repeating pattern in time instead of in space, like for normal crystals. One has also created wormholes, or at least claimed to have created wormholes on the QPU, and then latest here a couple of months ago was creating a state on the QPU that really emulates a chemical reaction, but just slows it down by a factor of 100 billion, so that one actually can follow what happens on it. And the interesting thing here is that this is not now simulations of a black hole. You don't do computations of how does a black hole or time crystal behave. You create that physically. That physical phenomenon takes place on the QPU, and that's very different from classical simulation, where so the borders between what is a computation and what is a simulation and what is reality really gets fudged when you use quantum computers, because these phenomena actually take place for real on the QPU. So it's not like in a classical computer where you just solve some equations and the computer tells you that this is how it would do it. It actually physically does these experiments there. Okay. Getting back to the HPC part, what tasks that require lots of computing power would be valuable for quantum computing? Well, one is compilation and transpilation of your quantum software, the quantum circuits. Especially when you get more and more qubits, then optimal compilation of the program itself becomes a highly complex optimization problem. And the reason is that we cannot just do a brute force compilation. We really need to somehow get as shallow and as error-resistant quantum circuits as possible. Because if the quantum circuits are too long, then the coherence time runs out before you have finished your calculation. So you really need to have super efficient optimization of the compilation already. And then, well, the whole process of this optimization becomes more complex just because, again, because quantum computers are not perfect. So all the qubits on your chip are different and behave differently and have different noise characteristics. So you really want to use those qubits in your algorithm more that have high fidelity and as little as possible those that you know that will probably introduce errors into your calculation. And this really becomes also a highly complex routing problem for when you build up and compile the circuit at really basic gate level. And then there's also this approximate compilations is becoming more and more popular, where one creates a mathematically almost equivalent circuit where then the errors introduced by some approximations to the circuit are considered smaller than the errors that would be introduced just because you have to do a longer circuit. And all of this really becomes problems for an HPC system already. We can compare this with just like the fast math or whatever flags in standard compilation where you are fine with having approximate answers to your double precision calculations as long as they are just executed much faster. And then there's error mitigation and error suppression. We'll come back to that, so I will not mention more of that. And in principle, also this co-designing of the whole integration. So we need to talk to each other, so as mentioned in the beginning. And this is just from the IBM paper now from when was it, May or something, where they claim to have this utility of quantum computing before fault tolerance. That's not the point of this one. The highlights here is to show that there's plenty to do on the classical side. The whole calculation here took, it says 4 hours, the whole experiment, but the actual quantum part of that was just 5 minutes. So, and most of the rest of the time was just this classical pre and post processing. And of course, if you want to do something efficiently, then you should get the classical part at least to run efficiently. So you don't need to do 4 hours of fudging around before and after. So that should be, in principle, instant, just because, well, you have supercomputers available, so you should use them and not just do it in a brute force silly way. Okay. That was a quick introduction. Then I'll just quickly mention 3 different ways of connecting HPC and QC systems. And so we have to couple somehow the quantum and the HPC resources. And this is work that is already taking place in many places around Europe. Also Japan and US are doing much work here, and one of the organizers of this workshop, the Nordic West project, has also already run several of these connected HPC-QC jobs. So it is work in progress already. And the reason why we are doing this is as mentioned, that we expect that in the future, handing out quantum computing resources will be standard among most HPC centers. And just in the following slide, so the idea is that the HPC center provides all of these basic user identity management and resource allocation and so forth tasks, and we just concentrate now on how to make the connection. So one can divide it into 3 different classes, which would be standalone, cloud access, co-located, where you have the quantum computer and the HPC on the same premises, and then this distributed version where the QPU or the quantum computer and the HPC systems are located separately, so there's some physical distance between them, and all of these come with different levels of complexity for the software stack, and that's or the middleware that connects these two, and that's why it's good to divide them into different ones. But just to mention first, one concept here is the latency that comes up with hybrid algorithms. You will do hybrid algorithms later on this school. Here's just a basic figure of how a hybrid algorithm works. So what you in principle do is that you make some sort of a Hamiltonian and then make a trial state that has some parameters, and then you evaluate some expectation value using a quantum computer, and then you use that value to adjust the parameters with a classical optimizer, and then you again feed these new parameters into the quantum computer that evaluates, and then you have this loop until you converge to some solution. That's the general rough idea of a hybrid algorithm. And now, when the quantum block and the classical block, or the calculation here, the blue box and the purple box, when both of them are fast so that they take little time to compute, then the communication has to be even faster, because otherwise communication becomes the bottleneck here in this. So if the transferring of data in these blue arrows here takes much longer than the calculations in these boxes, then it's of course unoptimal, because you want to do as much computation as possible and not just have these machines standing empty there. And now, with present QPUs, well, decoherence forces the quantum block to be fast, because the quantum computer will just crash so quickly that it has to finish the calculations in a very short time. And also because of the limited amount of qubits, then the classical optimization here for some tens of parameters doesn't take any time either. So this means that when we have these quick loops, then the standalone model, the cloud access model, really creates too much overhead. This means that we really have to have this classical processing somehow physically close, so that it can keep feeding the QPU with new things to calculate, new input. But this should be noted now that this is not any sort of a supercomputing HPC task. Some powerful server is more than enough, and that's what we have here in the distributed system. So we have this orange server that is physically located next to the quantum computer, but the proper supercomputer can then be somewhere else, because for the moment this purple box here is computationally not very demanding at all. So it doesn't really need to be a supercomputer in any way. A laptop even right now is more than sufficient. But anyway, the standalone system is out for hybrid algorithms. Okay, this is just quickly to show that when we actually get QPUs that can do something useful and provide quantum advantage by the definition of wall time to solution, then the runtimes of the quantum block will also increase. So here's just an example for the QAOA. So it's expected by some estimates, of course, this depends very much on the algorithm and algorithm development also, but anyway, that we are going to need circuit depths that are well beyond what is presently possible. So you will get up to needing to run about 1 million gates before you get quantum advantage. But when you run 1 million gates, then that already takes time. So which means that the blue box here will take at least seconds to complete. I think there's a calculation here. I'll just mention here quickly. So if you run 1 million gates, then already on a fast superconducting processor, then that will take about 100 milliseconds, and that's just for one shot. And you usually want to do some statistics, so you do this 1,000 times. It means that the classical resource doesn't really have to be very close at all. So in the future, probably cloud access will be again fine for many quantum applications as well. But low latency can be important also in the future when quantum computers mature. This is just one example of these hybrid algorithms where probably in the future it doesn't really matter, because if the calculation on the quantum computer takes a minute or two, then it doesn't matter if the communication takes 100 milliseconds or 2 milliseconds. But anyway, a separate server can take care of the classical computing that requires this low latency. And a straightforward approach is this co-location, where this server is just one of the nodes in the supercomputing center. But more involved is then this distributed method that we are also implemented in the Nordic West project and the upcoming LUMI Q project. So that's where we have this box that is standing next to it. But in a way, these are identical. So if we just would move the server box next there, it's the same thing. And then for this one, so it's just two sides of the same coin in principle. But it does require a bit more work to build a software stack for this distributed method, because there is need to take care of one additional communication step between the classical and the HPC. So we need to talk first between the quantum computer and this orange box, and then the orange box needs to talk also to the supercomputer for example, pre-processing and post-processing and sending the results and so forth. So that's not completely trivial how to do this in the most efficient way, and there is lots of development required still for this one. And well, also the user authentication needs to be done twice. So first when you log into the HPC system, and then you need to have some sort of credentials to be allowed to use the quantum computer, but that's rather trivial. Now Jake thinks it's not rather trivial, and Miroslav as well. But compared to the rest of the software stack, let's say, I should remove rather trivial. I should change that to easier. Yes. And well, then you also need personnel at more than one physical location, because well, neither HPC systems or quantum computers run independently anymore. Okay, but why would one then go through this trouble of building a distributed network? Well, the reason is that when you have this software stack in place, it's rather straightforward to add additional quantum computing resources, because all you need is to locate a classical server next to your quantum computer and an internet connection, and then install the software packages that you have developed on this. And this really increases the diversity of quantum computing resources that some given user has access to. So they can use QPUs from all around the world by logging into one environment, and then you also can do all sorts of parallel quantum computing schemes if you want to. And the reason here is one motivation for this is also pragmatic, and that's the quantum computers are very expensive for the moment, especially if we compare to what they actually can perform computationally. So not many HPC centers can buy all the 20 different quantum computer modalities and qubit technologies that are out there. And usually one doesn't also need to have a dedicated quantum computer at this stage at least. So it's much more resource efficient to share your quantum computer with others in exchange for getting access to another quantum computer. Because when you really develop your algorithms, as mentioned, so they will run in a completely different manner depending on if you run it on a superconducting one or an ion trap or whatever. So for the end user, it's more valuable to have part-time access to several quantum computers than have one dedicated quantum computer that they then can play around with. And another important advantage of this distributed one is that you really can have the quantum computer and the supercomputer located in environments that are optimal for each of them separately. So we can have HPCs in large data centers that have sufficient and affordable electric power. Especially the affordable electric power becomes more and more important here. And then we can have the quantum computers in shielded environments because, well, they don't like to be disturbed, so they should be shielded from temperature, vibrations, other noise sources, dust, whatever. All of these things that standard data centers are not very well attuned for. So well, the temperatures are high there. You have lots of vibrations from all sorts of sources and dust and everything. And so it's not very easy to install a quantum computer sitting next to a HPC system. And another one is that well, there was a paper some 2 years ago where they already started seeing that cosmic rays affect qubits and calculations, and which means that it might be in the future, when you have a high qubit counts, it might be necessary to really shield the quantum computers highly efficiently by, well, I don't know, digging them underground or putting them inside boxes that really shield against cosmic radiation. And this is, of course, not something that you usually want to do with large supercomputers, to dig it underground. Of course, there are data centers that are located already underground, like in Norway, but normally you don't have them. And then just quickly, well, I'll just show this and go on. But LumiQ is one of the 6 EuroHPC projects that will now give access to quantum computers for all EuroHPC affiliated countries, which means the whole European Union, plus some additional member states. And here the idea is to really build up this type of software stack. I'll just quickly show this for mostly for the purpose of showing that when we want to do quantum computing, there's lots of classical programming still needed in all sorts of levels, so both on the algorithm side and then on the interface side and so forth. But the idea is to connect the IT4I Karolina supercomputer in the Czech Republic to this quantum computer that is being procured here. And here we also have this orange box from the previous slides that really keeps feeding the QPU there with data and then also does error mitigation and whatever. But the idea, as said, is to build up a software stack that doesn't really care what kind of supercomputer system we have and what kind of quantum computer we have. So it should be general enough so that when we have built that software, then we can, in other projects, just quickly add all of these other HPC systems and quantum computers to it to have this really cross-coupled HPC-QC system in place. Okay. Then to the final part of the talk. So on error mitigation. Why do we want to use something called error mitigations? Well, as mentioned, so quantum computers compute wrong most of the time. And the long-term ultimate goal is to produce these logical qubits out of several hundreds or thousands of physical qubits. And these logical qubits would be these perfect qubits that have, in principle, very long coherence times and then almost zero error, so almost 100% fidelity. And many algorithms in the form that they have been presented assume that we have logical qubits available, but we are actually very far from this reality. And this is just from the Google AI blog, based on their one of the papers that they had there was in March this year, which just shows their roadmap of how to come up to really some sort of an error-corrected machine. And then what we can see here is, well, for the moment, the error that we have, or the fidelities that we have, is then about 99.9, so 3 nines fidelity. With that, you are very far from doing error correction or having any sort of fault tolerance. In practice, it means that 1 in 1,000 operations fail, and then that's might sound like, oh, that's not that much, but when you think of how many operations you actually need to do to actually produce some interesting results and execute your algorithm, then you realize that, well, if on average 1 in 1,000 operations fail, then you really cannot do much at all. And that's also the reason why it's easier to perform these quantum supremacy experiments, where you just make some sort of a random circuit that then does something that will be very difficult to simulate on a supercomputer, but they are worthless from the point of view that they actually cannot perform any interesting calculations, because all interesting calculations would require significantly more gates. gates in your circuit to be executed. So we need to come for proper error correction. Well, they estimate that we should have at least, or Google estimated convincingly in the paper that we should come down to an error of at least 10 to the minus 6. So that's 3 orders of magnitude better quality qubits than we have now. So it will not happen tomorrow, and it will not happen in 3 years, and it will not happen in 5 years. Now I start sounding like Göran. It will not happen ever. But let's see. I'm personally I'm positive in the way that it is more of an engineering problem than a actual problem. But solving this engineering problem. Apologies to all the engineers. But it's not a fundamental problem. That's what I mean. So it will require lots of ingenious work to really figure out how to get down to these errors. But I believe it can be done with the help of clever people. But anyway, so this figure shows that where we are now. So we have about 100 qubits and very, very high error rates in a way. Well, Google estimates that they would have one long-lived logical qubit after 2025. And after that, there's not even any estimates of the years there. So it is a complex problem. That means that we actually need to learn how to deal with this and how to cope with the NISQ, or the noisy intermediate scale quantum era that we are in now. So we need to somehow figure out how to get something useful out of quantum computers, even if they are imperfect. So deal with the noise, and that's where this noise mitigation or error suppression, error mitigation, whatever you want to call it, comes into play. And also, we will not talk about that, but algorithm design is an important part of this. So you also need to make your algorithms from the get-go noise resistant and figure out how they can deal with this. But just in the few minutes that are left, so a bit about error mitigation or suppression. So it means, well, there's several ways to do it, but one is to learn or machine learn when it becomes complex the error characteristics of the quantum computer that you have. And then you correct for the noise in post-processing. So you do the calculation, and then you somehow filter out the noise and enhance the signal. A bit like in classical signal enhancing processes. And the example we are going to have here today is just a simple readout error mitigation. And to do this, what you need is, so you have to characterize the errors that are present in the quantum computer. And for this readout error mitigation, then it's especially the readout error. And the readout error just means that when you measure a qubit, and it should return 1, but the readout algorithm or method returns at 0, and the other way around. So it gives the wrong output. And this actually is a problem, and it does happen, and that's why we need to take care of this also. Okay, the full proper characterization really scales exponentially with qubit count. So it means that, well, you cannot really use it for as is and as will be presented for a very large number of qubits. But otherwise, it's very simple to implement and use. So you don't, for example, need to do any sort of modifications to your circuit. You just run it as is, and the noise mitigation process makes your results better. Here's just a picture from this MITIC library that you can. I'm not sure now if it's available for Qiskit, but at least it's available for Circ. Okay, it's also for Qiskit. But it's a package that you can install on alongside your Qiskit or Circ framework. And well, it just shows easily here. So, well, you have a quantum program, and then in generated circuit. This is now general because they have several different noise mitigation models there, but okay, they just mention here that this is trivial for the readout error mitigation because, well, you don't do anything to the circuit. And then you run it, and then you get, we'll see how you do it, but you just get a better result by using this inverse confusing matrix, and then you have an error mitigated result. Okay. So the idea is, as said, so that you should learn how the quantum computer readout goes wrong. This means that you need to sample how the output of the quantum computer differs from what it should spit out. So this is just a quick example for 2 qubits that I did yesterday. So we have a 2 qubit simple circuit where we just have the bit flip. So we know that, well, or do we, what should the result after this be? Well, obviously it should be 1, 1, more or less obviously. So you start from 0 and then you flip that 0 state to a 1 state and then you measure. But when you actually do this, then you can see that, and this is now done with 1,000 shots, you can see that, well, not all of the 1,000 readouts give the result 1, 1. It's a rather good result for modern day quantum computers, but it's not perfect. And this is, so you really get even 0, 0 in some cases. But this shows that the quantum computers are not reliable. But you can fix this. And you do this by using a confusion matrix or error matrix. And the example I put here is now just for simplicity. Let's assume that the quantum computer is much worse than HELMI, and the readout error is 25%. And then the confusion matrix, which just well, the name comes from machine learning, I think originally, and the idea is that it shows how the results differ from what the expected ones are. So how much confusion is there in the categorization of your results? And so if you can keep this one here now somehow for a while, but okay. Anyway, the idea is that you put up a matrix. In the upper left-hand side, you have the probability of measuring 0, 0 when you should measure 0, 0. And below that, you have the probability of measuring 0, 1 when you should measure 0, 0, and so forth. And in the second column, you have the same thing. And what we can see here is that if we would have no error, then this would be diagonal identity matrix with just ones here on the diagonal and zeros everywhere else, because then when you should measure 1, 0, then you would always get 1, 0. But now if we have a readout error of 25%, then our confusion matrix or error matrix looks like this. So the probability of measuring 0, 0 when you have 0, 0 is just 0.75 times 0.75, because you have a 75% probability of getting the right result. So the total probability of getting the right result is just 0.56. And the probability of measuring 0, 1 when you should actually measure 0, 0 is then 0.75 times 0.25, because there was this 25% error that one of them is wrong. So that's 18% probability. And then finally, then the probability that both of the measurements are wrong is, well, 25% times 25%, so 6%. And then you just do the same calculation here over and over, and you can see that, yes, we have the highest values are here on the diagonal, but actually you only have about a 56% probability of getting the result that you should get. Okay. So now you have this confusion matrix that characterizes the error in your quantum computer. And I just want to mention that if you want to do this for HELMI, for a real quantum computer, then just, for example, this calculation would give you the values of the last column here, because you should measure 1, 1, but these are what you actually measure. So then you can just put the probabilities into the last column here. And then you just simply to characterize it further, the other columns, then you just remove one of these x's until you have nothing there, and you should just measure zeros, and you will see that you will not measure just zeros. Okay, this of course assumes now that we only have readout error. So which is not true, and it just shows that it gets more complicated because now we assume, for this characterization, we assume that this not operation here is 100% perfect, which is not. We also assume that the initialization of the qubits to 0 is perfect, which is not. We also assume that the idling time here in between introduces no errors, which it does. So there's lots of different errors that come on top of each other, and really singling out what error is now giving the wrong results is very difficult in itself. But now just for the purpose of seeing how this in a simplified world works, so that's where this version works well. But anyway, now when we have this confusion matrix, then we want to take its inverse so that we then can correct the results. And the inverse or pseudo-inverse, just in case you cannot invert it properly, of this confusion matrix just looks like this. And if you don't want to do the linear algebra yourself, then like me, then there's this nice online calculator that does all sorts of matrix operations and also shows the steps of how to do them. So just go there. But for the purpose of this example, so we have this inverted matrix looks like this. So what we do then is that we apply this inverted matrix on the vector of results. So in a simplified version, this M0, 0, 0, 1, 1, 0, 1, 1 is just the counts of how many times did you measure 0, 0, 0, 1, 1, 0, and 1, 1 in your whatever circuit that you run. And then this inverted confusion matrix will correct the numbers here more towards what it should be. And this actually works surprisingly well. And there will be, in the afternoon, you will see a demonstration of how this actually works on a real quantum computer. Jake will show it. But it is conceptually a very simple correction, but it does increase the fidelity of your final results surprisingly much. Okay, for those who actually know linear algebra a bit more, we should note that if we just apply it in this simple manner, then we can end up having negative probabilities or negative counts for these because we have negative values here in the matrix. So, and of course we cannot measure -5 times the state 0, 0 in a real experiment. So then you somehow need to ensure that the final vector here has just positive values, and then there's more or less advanced ways of doing this. So you can just distribute all the negative values evenly or weightedly to the other measurements or whatever. But in principle, it's not more complicated than this. Oh, I'm over time. So good summary. One summary is that I want to point out here is that for making quantum computing useful, there's lots of classical software development that needs to be done. So one doesn't need to only do quantum algorithms within quantum computing. There's really a big amount of work required just on classical programming side. Also, one needs to start making existing workflows quantum ready somehow and introduce some sort of a dynamic shift in your workflow so that the more quantum computing capacity there is available, the more of your workflow can be offloaded to quantum computers to increase its usefulness and efficiency. And then we should remember that quantum advantage actually is already here. And especially from the HPC Center point of view, then it's important that we onboard those users that already can get something interesting out of quantum computers. And especially now when we can make these quantum computers available to a much larger group. So there is, of course, those people who have their own quantum computer in the university lab and can play around and fiddle with it and do whatever experiments they want on it. But now, through making it available through HPC centers already, many more people can perform these experiments. So you don't need to belong to Miroslav's group to be able to do these experiments. But when you connect this quantum computer to be more available more widely, then other people can really start doing all sorts of cool physics experiments already now. And then, well, as we know, so quantum computing is high risk but also very high gain type of project. So to be honest, we don't really know when quantum computing will really break through, but when it does, it will be it will change at least the software and computational modeling world significantly, and thereby also to end on a high note, be very beneficial to society. Thank you.
Mikael, that was super interesting. Do we have questions from the audience?
Does HELMI have built-in error mitigation?
We will see that in the afternoon. If it has built-in, no, but you can implement on the software side your own error mitigation there. Yeah.
A question on the errors. So you assumed here that the readout error is symmetric with respect to 0 or 1. Is that the case, or how much does it differ? And how?
No, it doesn't have to be, because the general one looks like this. This doesn't have to be symmetric, no. It was just the example, then just for simplicity to show it, then both of them had 25%. But it doesn't have to be, so you can have different probabilities.
I understand that, but so if you take HELMI as an example, is the state of the qubit and the readout error uncorrelated with the state? And the second question is, do you have readout error that is correlation between qubits?
Maybe I'll let Jake reveal the details of HELMI, but I don't know how much I can talk about
so in this case, the example that Mikael showed, they're independent. The qubits are assumed to be uncorrelated. There is a more complicated example, which I've also not decided to show later on, which assumes that they are correlated. But the problem with this is it scales with the number of qubits rapidly. So with 5 qubits, it's fine, because you would have to calculate all 32 different matrices, but then as soon as you get to 20 qubits, you're calculating almost 1 million, and it doesn't scale very nicely. And then what was your first question? Yeah, so the readout error assumes. So when you have your qubit, you assume with readout error you're only mitigating the measurement when you finally want your state out. Therefore, you assume that you actually prepared your qubit correctly. You could have a case where you prepared a qubit in the 1 state initially, and therefore you cannot really mitigate it at all. And this is a case of what we call state preparation versus measurement error. And there are error mitigation schemes for state preparation as well. And HELMI also has this built in, but it's also the problem is again scalability.
Yeah. So as mentioned here, so it does scale like exponentially. So making this, if you just have 2 qubits, then you just need of course this 4x4 matrix. But if you have 3 qubits, then you need an 8x8 matrix. And if you have 20 qubits, then you need a 1,000,000x1,000,000 matrix. And to characterize those errors, then to get good statistics, then you should measure all of those different options, well, let's say 1,000 times. So then you need to do 1 billion circuits just to characterize the error. And before you have run that, then you need to recalibrate the machine, and so you don't really get anything out of it. So, so you have to do it in practice more locally when you have more qubits. Also the other one, so yes, as Jake mentioned, so it's very difficult to tell the difference between the state preparation error and the readout error, because, well, if you want to measure the 0-0 confusion matrix, then you would just, in principle, put your qubits into state 0 and not have this excess here, and just measure it. But then you actually measure both the state preparation error and the readout error, and you don't really know where did the error occur. So then you have to do, if you really want to characterize it, then I guess there are some more complex ways of doing more complex circuits to see what actually happened there. But really, all the errors are correlated. And even if they would not be correlated, then figuring out the components of what comes from which error is very complex. And that's why we really, and all of this, figuring out this is also just classical programming and classical algorithm development and figuring out how to characterize errors. So there's again, plenty of classical software development and idea development needed. But this is a very intensive field of study because I think most players now have understood that this error mitigation and is really what we need to have in place to get some sort of quantum advantage before we all die.
But I mean, it's a little bit weird. So running the quantum computer is applying a unitary matrix to a state vector, right? So that's what we get out of the quantum computer. And your suggestion is to correct the result by classically applying a matrix or computing a pseudo-inverse, applying that to the output state vector.
Yeah, but
So
in the readout error, that you don't really apply any sort of even mathematically any matrices there, and you don't do any manipulations of the qubit. You just measure its state somehow, and then you will get the 0, 1. So that's not a gate operation as such.
Okay, so you never have to apply the pseudo-inverse on your readouts.
No, on the readouts, that's exactly where you do it.
But that
because
matrix has the same size as the unitary matrix you applied on your state vector. It scales exponentially with your number of qubits. So
to get the inverse.
yeah, no, to apply the inverse, computing the inverse has another order of magnitude in complexity.
Yeah, sure. Yes. So both the characterization and what multiplying a million by million matrix with the vector, so that takes no time. So the problem comes much later than for the characterization, because this calculation, well, I don't know now. Now Sven can probably tell how big matrices are easily done on supercomputers these days, but I think we can easily go to a billion times billion matrices
No, I'm just
times a
pointing out,
vector.
So why would I run the quantum computer at all? So running the quantum computer in a simulation on a classical computer would be this matrix vector multiplication.
No.
Okay.
No, well, because now you can use this inverse of the confusion matrix for any circuit, and not only for the one that you use for characterization. This is a simple one where you're just supposed to get exactly 0 and you know the answer. But the confusion matrix, or the inverse of it, corrects any arbitrary output vector here that you have. And so this M here can be any the output of any algorithm, and this one will correct that. So it will correct the distribution of these measured. And this is now, of course, just a 2-qubit version, but you could have 20 of them here. So in that way, it's useful. So you're not only repeating the calculation of this one. You use this simple algorithm just to characterize the noise, but then you use the confusion matrix to correct for any algorithm that you're running there. I don't know if that answered the question.
One question from our online participants, although it seems that it might be Göran Vendin who actually asked it. So, Mikael, I guess you noticed that 1 week after the Kim IBM 127 qubit Nature publication, Tyndall and collaborators published a paper using classical tensor networks to compute the same result. What do you make of that?
Well, I would say that IBM wanted to hype it too much, but the idea of the paper, it was mentioned here somewhere, I think, was more to show that you can do. I had somewhere about this. That you actually can get better expectation values with error mitigation. But the algorithm as such, yes, it was shown in at least a couple of papers after this that the actual circuit that they are running will be solved if you allow for error much more efficiently on a laptop. Yes, but yes, they wanted to overhype it. I think I like to think that the scientists here are honest, and the overhyping came from the marketing department. But the main point of the paper, as I see it, was not to show that their 127 qubit machine now does something faster than supercomputers. It was really to show that error mitigation can improve the results.
Now I am very happy to introduce Miroslav Dobsicek.
Dobsicek.
Yep. who will tell us about the software stack for quantum computers. So over to you.
Thank you, Tor. Hello, everyone. Good to see you. Yeah. So my name is Miroslav. I am working here. I'm employed here at VACT or Wallenberg Center for Quantum Technologies here at Chalmers University, and I'm also affiliated with multiple European projects. Basically, effectively trying to really sort of build the quantum computer from the software part. So that's what I will be talking about. Okay, and this is the quick overview of what I will touch upon. So I will sort of tell you quickly what is a software stack in my world, because there are multiple different ways sort of where you cut the line where software stack ends and start. And then I will also hopefully get, if the time allows and my timing is good, a little bit down to the hardware level. And yeah, hopefully you will get good experience and good overview of what's going on in this field. Yeah, so this is very nice slide, one of my favorites, which I'm often using in the presentations when I give them, and it sort of gives you really the 4 pillars which are there, and that is the high-level circuit design, then some sort of compiling, going to control level pulses, and then the hardware instruments themselves, which are typically sitting somewhere in a lab. And what is nice to notice here is that up until recently, the 2 lower parts were really like a domain for people doing hardcore physics, those who sort of know how to operate instruments in the lab, and the 2 upper boxes were like a specific domain of people from computer science. And these two groups, they did not really talk much together. And that was supposed to there was this disconnect between, okay, this is really physics, there is not much to do for computer scientists, and on the other hand, people from computer science, they sort of like this abstraction of having some sort of set of universal gates. From that, it sort of resembles this logical circuits or some sort of Turing machine approach. And they looked at the complexity classes, and everybody was happy, except that there was not a working quantum computer, because these 2 groups did not, and also in practice could not work together because there was a missing link. But right now, with the upcoming investment from national states and also from European Commission, basically many national states are now able to procure or build their own quantum computers. And with the sort of European-wide access, hopefully in a couple of years, all of us will have some sort of access to these demonstrators and try things ourselves. So that's exactly like where the build-up of current software stack fits into, to enable remote access and enable sort of simplified access, which doesn't require you to know too much of physics. Good. I hope that after the first day, and probably also from your previous studies, you already know that there is something called a circuit model. And as of now, this is more or less the only model for quantum computation we have. There are some other small approaches, but this is still like the only model which is really widely used. And so for that reason, the software stack is basically built around this notion of a quantum circuit model. So what I will mostly cover in my talk is sort of what's basically above, how do we get some circuit, and then once we have a circuit, how do we actually run it, what happens afterwards. Good. So starting with the high-level parts. So basically asking how do we get some circuits, because we don't really want to draw them by hand. You can for 1 or 2 qubits. That's what people did up until recently. But now we mostly want to generate them. And if you are new to the field and sort of just want to try out things, you actually can, because there are existing couple of fairly generic methods which allow you to basically take your classical problem and encode it into one of existing quantum methods, which sort of provides you a generic speedup and just see what happens. I think classically this would be very much like trying to throw, let's say, this Boolean satisfier debris solver on your problem. It might work, it might not, but it's quite simple to sort of encode more or less anything into some sort of SAT solver. Those of you who are fond of modern AI, you know there is something called a transformer. Again, it's a fairly generic method. If you like, you can sort of take any classical problem and just throw a transformer on it and see if you get lucky or not. Yeah, if you are then a little bit more advanced, you sort of you may choose to attack the problem directly, meaning that you actually design your own quantum algorithm, but it's fairly difficult. So let me dive a little bit more into these generic classes. So as I said, it's all about encoding. So you take your classical problem and just choose sort of one of these fairly generic approaches and see if it helps. And as of now, there are these 4 fairly generic classes. I think you have probably heard some of these names. At least the QAOA stuff for optimization problem is fairly well known. You have also probably heard about quantum Fourier transform, which is behind the Shor's factoring algorithm for large numbers, which more or less started this whole field. Grover algorithm, it's a generic speed-up search problem. And probably a little bit less known, but of quite good importance, is this HHL algorithm, which allows you to solve a system of linear equations. So the reason why this is it's one of the newer algorithms, so that's why it's a little bit less known. But when it comes to, for example, connecting this HPC-QC system, as Mikael told you before, this algorithm might be one of the more useful ones, because sort of solving a large set of equations is a typical HPC task. And if you can offload parts of those problems to some sort of quantum accelerator, it might work. Good. Then the second way, how to get to some quantum circuit, is actually take the classical path through classical reversible logic. I guess most of you probably are familiar with some basics of classical logical circuits with these non-XOR AND gates and others. And with that, you probably know that there exists basically a corresponding reversible counterpart for all these gates. And the moment you have these reversible counterparts, more or less for all these reversible parts, there already exists a corresponding quantum gate. So one way how to get to a quantum circuit is just that you take your classical algorithm, break it down in terms of gates, turn it into reversible gates, which more or less means that you just need to add some extra input and outputs occasionally to keep it reversible. And with that, you suddenly end up with a matching quantum circuit, which works over superposition of quantum state, which is kind of magic. And this is not well known between people who don't study this problem. So I hope you will remember that this actually exists. Good. Yeah. Next thing you can do is to try your luck with something called automatic decomposition. So this would probably be similar in a classical word, like trying these Boolean satisfiability solvers or something like that. In short, what I'm trying to say here is that you have some mathematical problem. For example, you want to perform Fourier transform, and it's quite easy if you are a mathematician. You sort of know what kind of transformation you want to perform on your state. I mean, this is basically your starting point of what sort of transformation or calculation you want to perform. So you just write it down as a formula, and then it's relatively straightforward to sort of expand this in a matrix form. Yeah, I guess you are probably familiar that the moment you have sort of matrix, you can see it as that rows can be seen as an input and columns as output, or the other way around, just depending on your preferences. So you have basically just expanded the formula into a finite dimensional matrix, and there you go. So with this matrix now at hand, you can sort of apply some fairly generic decomposition problems. One of the more popular is called single error decomposition, and sort of hope that this large, exponentially large gate in terms of qubits will end up being broken to some more trivial gates, effectively hoping the gates which can be directly executed on a quantum computer, and hopefully it will work. Unfortunately, unfortunately, there is no guarantee that you will sort of end up with a circuit where the length is actually reasonable, efficient, or polynomial size. You will most likely end up with an exponentially long circuit. I mean, that's sort of like the price for trying a generic stuff. But I also hope that many of you now suddenly see the problem or immediately realize that if this actually would have worked, that you would always, by automatic decomposition, would get an efficient circuit. Then we don't have any problems left in the computational world. because that sort of implies that you just state your problem and there exists a routine which finds automatically a fast, efficient algorithm. And yeah, it doesn't appear that this is the case in the world we live in. There seems to be these classes of polynomial and exponential and p-space problems. Yeah, it doesn't appear that everything just collapses to simple stuff. Good. And then the last thing is, yeah, so if you are get bored with just using generic stuff, something somebody else have done for you, you can try your luck to design your own quantum algorithm, but it's really not an easy task. As of now, more or less after Shor algorithm in the 90s, there have been some improvements, some of these new algorithms, as I mentioned, like for example the one for solving the system of linear equations, but otherwise people did not really succeed in finding something like, basically there is no second breakthrough after Shor. We are still a little bit stuck with exactly the example, trying to generalize, trying to bend it somehow, and yeah, it's a difficult problem. And part of this problem is coming from the fact that our understanding with this of this quantum computing sitting on the top of, or more like being embedded in quantum mechanics, is that we still have this notion of sort of playing with vectors in a complex Hilbert spaces. And that's not exactly intuitive environment for actually thinking about computational problems. It's kind of okay environment for thinking about vectors, but when it comes to trying to envision something more complex, it doesn't really work. It's very much like in the past, or when John von Neumann and people around him built ENIAC, they have been a little bit chasing bits around. Yeah, and it's difficult to really come up. I'm pretty sure that people who, when they built the first computers, they could not really dream of internet or anything we have nowadays, because just the moment you play with handful of bits which barely work, an imagination of high-level algorithms is very difficult to get by or come by. Yeah. So right now, if you are about to, I don't know, if you want to do PhD or postdoc or just sort of, I don't know, join some research institute and you want to do something in this field, what is like more hot is to work on these error correction codes. There is a good progress, there is a lot of good math, and then also these complexity classes which sort of tries to figure out where exactly the assumed computational power and the speed up may come from. Yeah. And then there is also one quite almost funny field, which is nevertheless quite interesting, is to finding new classical algorithms by dequantization. So what this means is that since quantum computing is basically a little bit, yeah, it is more powerful in some sense. So you can basically try to attack your problem with this enhanced power, and then you try to figure out, okay, and if you get basically a faster circuit, you can try to just basically say, okay, where does the speed up come from? And you try to remove these quantum essence one by one, possibly by just probabilistic sampling. And it often turns out that you can find better classical algorithms by going this route. Yeah, this is also like, for example, what has happened when there was this question about this 127 paper by IBM, where Mikael mentioned that, okay, so IBM actually ran it, and then it was immediately sort of like, yeah, other people said, I can do this with tensor network as well. And so this happens fairly often, that the moment people find some advantage with quantum, fairly often, basically the classical people, when they realize the conditions, they basically can just, okay, where does the speed up come from? And fairly often they are able to remove it and get a better classical algorithm than we had before. All right, so now we know how to get a circuit, either by your labor or using other people's labor. So now the question is, what sort of happens once we have the circuit? And the answer is that when you generate a circuit, it's hardly ever optimal and ready to be executed. So what you need to do next is a couple of optimization and compression and whatnot, things to sort of minimize the circuit so that it's shorter and you actually have a chance to run it on your short-lived, noisy intermediate device. So you want to make the circuit shorter. You also fairly often need to map it to the native gate set. And so this has to do with the fact that there are multiple competing quantum technologies which are using slightly different physical phenomena. And these slightly different physical phenomena are leading to slightly different native gate sets. But it's quite hassle-some for computer scientists to sort of work with native gate sets because they are different for different architectures. So computer scientists typically work with some universal gate set, and then once you get the circuit in the universal gate set, you want to map it to the native gate set. Yeah, so these are the things which has to be done. Also, fairly often we want to insert some error mitigation gates, which can also be as simple as, for example, when you only have a qubit, it tends to decay faster if you don't drive it. So it's, for example, easier if there is like an identity on a circuit that you don't want to do something for some time. It actually might be easier just to apply, let's say, 2 X gates after each other, which is logically identity, but in practice you actually drive the qubit and it survives its coherence time for a little bit longer. So that's also one method how to error mitigate. Good. So I will just quickly go through these methods. Maybe you have heard some of them. I hope that I will still be able to tell you something new. So when you want to do the compression, one of the most common methods still is to sort of look for circuit identities. So if you, for example, use Circ, Qiskit, or Penlane, or any of these user space tools, there is fairly often already an existing library of well-known circuit identities. And then the optimization sort of works by the compiler or optimizer goes through the circuit, basically does a pattern search, replaces, and then again and again and again. Yeah, there are also more modern methods, but nothing really helps. So the moment you generate a very long circuit, you can sort of, with these methods, compress it by 5–10%, but nothing will really get you from 10,000, which is typically what Qiskit will generate for you in case of like this QAOA, and get to few tens of gates, which is what you can physically execute on a quantum computer. So there is no magic wand. It's hard. Good. Yeah. This I have almost already mentioned. So you have the common gates or universal gate set, and you want to map it to the existing or the native gate set. So it's fairly often the case that at least in superconducting circuits that we can implement rotations around Z and X axis. So any other single qubit gate is then decomposed in terms of rotating along 2 axes. Typically it's Z and X. Yeah, and then also, as I've already mentioned, this decomposition. Sometimes I basically told you that it's not really the way forward to try to decompose big matrices and hope that it will somehow magically generate a good circuit. But if you already have a smaller circuit and you just want to decompose for the sake of going to another gate set, it can actually help. Good. And here is a small example with Qiskit. So what I want to show you here is just the unrolling. So I have a very super small circuit with Hadamard gate and Z gate. And I want to run it on one of the backends, IBM Manila. It doesn't exist anymore. I think it was retired last year or so. Doesn't matter. Slide still holds. So I checked the basic gate set or the native gate set of this particular chip. And you see that it doesn't support natively Hadamard or Z. It supports something else. Rotation around Z-axis, square root of X, X, control X, and reset. Yeah. I transpiled the circuit with respect to the backend, and this is the transpiled circuit. You see that it just works. You don't really have to do anything. Good. Next thing is optimal routing. So this has to do with the fact that when you have your logical circuit, you sort of expect that every qubit is connected to any other, that you can sort of apply just coupling as you go. Nevertheless, the physical layout of the qubit typically is not all-to-all, because that would imply too many of these couplers. And if you put... Okay, sorry. Yeah, so that would imply too many of these couplers, but if you put too many of these couplers on the chip, it leads to too much of a crosstalk, increasing the noise. So there is a ratio of benefits, sort of how dense coupling map you want to provide in your circuit. So this problem of optimal routing sort of tries to address the problem how to take the logical circuit and map it to the physical layout matching the chip. Because if you don't have a direct coupling, you have to apply swap gates, and that sort of costs you time because then you have to swap all the time. Classically, this would fairly well correspond to the situation that you have all your data in your main memory, and then you have a CPU. And basically, when you have something in your memory here and there, like in one location and another, you cannot really do computation in the memory directly. What you do is that you copy the data to a CPU register. Then the CPU register acts on the data, and then it copies the result back to the memory. So we cannot really basically doing copying in quantum world because that would destroy information. So we do swapping, but it's effectively the same thing. You just cannot easily talk any qubit to any qubit, very much like in classical PC. You cannot talk from one memory location to another one directly. You go through CPU and then copy back and forward. All right, here is just a live, not live, but a practical example how just Qiskit does this for you. So again, the reason why I've chosen Manila chip is that it's actually a linear chip. It's not even a lattice square. It's just a linear chain of qubits. I have a circuit which you see I'm jumping over qubit 0, or over qubit 1. And after unrolling and compression and routing, I got a new circuit which sort of maps nicely to this particular layout of the chip. Yeah. Again, it just works, at least on these small examples. I should also tell you that this problem of routing is one of these NP complete problems. So that's more or less like the case with everything with the circuits, because the circuits can be seen as a graph, right? It's just boxes and wires between, so it's a graph, and more or less anything which has to do with the graph theory almost always leads to NP complete problems. Yeah. So if you do this on a bigger chip, your laptop will just sort of go wild for a night, and maybe something good will come of it, maybe not. Okay, good. So now our gates are optimized. What do we do next? So next thing is try to execute it. But how do we do that? Because right now, assuming that, let's say, for example, we are in Qiskit, we have a circuit, but the circuits right now in the Python sort of lives as some object in some memory. And the representation of the circuit sort of doesn't really mean anything outside of the Python interpreter. So how do we move on from this internal representation with some runtime of some language to actually run it? So yeah, the answer is quite simple. We basically take a textual or binary representation of the circuit. Textual is easier. And once what you do is that basically you convert the object to a piece of text. Yeah, this is typically what is now. I wanted to say typically, and so I wanted to sound it like I know. I've forgotten the word. How's it called? The JSON object. Guys, help me. So when you have an object in your programming language and you want to send it over network, serialization. That's the work So you want to serialize your object, effectively stringify it so that it can be transferred over network. Yeah. So this is exactly what we do here. And the current standard is called OpenQASM version 2 from IBM. It's also not really much of a standard because it's very directly maps and connects to the circuit model. So basically it's really just a question of deciding whether you write Hadamard with lowercase or uppercase letter, whether you include semicolons at the end or not. So the language is fairly trivial. So it is a standard, but at the same time it's not much really of a standard because it's trivial. Still good to have. All right. And now what happens if we want to run it on a simulator? Because that's typically what will happen if you don't have access to the real stuff. Yeah, I will just pass through this very quickly. So what happens is that these gates, they get expanded to matrix representation. And the reason why I'm basically bringing this up, but I don't want to really spend too much time on this, is that sometimes people a little bit confuse the qubits and the quantum gate with their matrix representation. But a qubit is not really some sort of vector, it's more complicated, and a quantum gate is not a matrix. It can be represented by the matrix, but it just corresponds to some physical process. And yes, it can be represented by a matrix, but that's not the same thing. Good. Let's go to a real device. So here we have a software stack. So as you can imagine, we sort of have all the typical suspect, like some sort of remote API. Nowadays, typically we go for just REST-based web interfaces because they are so easy to implement. Everything is ready, and also performance on these interfaces is not the bottleneck. The quantum chip sort of performs much worse, so you don't need to be much bothered whether REST API is sufficiently fast or not. Then, yeah, semi-obviously there is some sort of control software stack where you have queuing, you take care of users, you store somewhere results. And then it becomes a little bit more interesting. So there are some instruments in the lab. They need to be synchronized, they need to be pre-programmed with these microwave pulses. So that implies that there is a layer called instrument orchestration. And after that, we are sort of going with the hardware equipment. So there is a bunch of microwave instruments. I will then show you some pictures as well. And there is cryogenic equipment. That's usually what you see, this fancy golden wiring, what people typically put on their slides. And like, this is a quantum computer. It's not, that's just a cryogenic equipment. I have specifically resisted to put such a picture on my first slide. And then there is the quantum chip. Good. Now to make the abstract boxes a little bit more tangible, I've just put some real components which we are using in our lab at Chalmers. So on the instrument side, we are fairly often using instruments from a Dutch company called Qblocks or from a Swiss company called Zurich Instruments. Then when it comes to the instrument orchestration layer, we are currently using a tool called Quantify, again from a Dutch quantum ecosystem. It's open source, very nice. And then with ZI, we used to use a tool Lubber, but that one is retired now. I think you cannot buy it or download it anymore. Yeah, and then like on the practical side, when it comes to being close to the real backend, we are using Redis to store a few thousands of our runtime parameters around the system. And as we are approaching towards the user, then we use MongoDB because that one natively saves these JSON collections. So it's a nice match. Not that it's somehow super good, but it's good enough and easy to use. And then yes, we are mostly focusing on supporting Qiskit users at Chalmers. All right. And now we are getting down to the real hardware. So yeah, here's a piece of the fancy wiring in the cryostat. And as an example, I've prepared this small circuit, which just sort of has only 2 qubits. And this is a corresponding pulse sequence to run this small circuit. So this is a part of the compilation from gates to pulses, which happens in the control stack close to the backend. And yeah, to help you decipher a little bit what you actually see. So there are 2 qubits, qubit 0 and 1, and that matches with the drive line D0 and drive line D1. So those 2 lines corresponds to pulses sent to the qubit. And then we also have a coupler for the control X, and that corresponds to the drive line core U0. So that's the pulse. And then we have a readout, and that corresponds to the measurement M0 and AO. Yeah, so this is the pulse schedule which sort of needs to be prepared on the side of a control PC. This is then pre-uploaded to the control instruments. And then when you have done this, you also program the instruments to basically play these waveforms with a specific timing and alignment. And this is an example of something called Q1 assembly. So yeah, this is once you have uploaded the instruments, once you have uploaded the waveforms to the instrument, you tell it wait, play, wait, play, synchronize. That's about it. So this is like the lowest level. And I should also tell you that, for example, at Chalmers, we are not really dealing with assembly at this level. This is automatically generated for us. So we as experimentalists prepare the pulses, but then the compilation of sort of how to upload it to the instruments and how the instruments will synchronize it, that's sort of handled by a compiler for us. So we don't have to write this manually, that's my message. All right, and this is my last slide. So this is our latest and largest 25 qubit chip, which we have designed and manufactured and now also measure on at Chalmers. You see that it's a square lattice layout. Yeah, it's also good to know that it's so-called flip chip design, which means that we are actually gluing this chip from two chips. So there's a quantum chip, the upper one, and then the control chip below that, because not everything really fits nicely in the planar design. So what we are currently doing is just gluing these two chips in this flip chip manner. All right. Yes. And here is then how it looks on a photo. Okay, that was all what I wanted to tell you today. And you will also have a chance to talk to me through the day. I will try to be here around. And then in the afternoon, I also have a small hands-on session where I will guide you through a little bit of a small experiment on a quantum computer, explaining a little bit in more details how a pulse goes into readout resonator and how it enters the circuit and sort of what kind of response you can measure. And then at 6 o'clock, I will also, at Chalmers, I will give you a guided tour in our lab. So you will have a more chance to talk to me. Good.
Outstanding. Thank you. Just on that point regarding Chalmers tonight, so make sure you show up at 6 o'clock because the building is locked, and we should all be there at the same time so we can get let in. But there's time for questions to Miroslav. Any questions from the room?
A very naive question. So you show these nice text format for all the circuits. So I noticed that the input vector there, input state vector, is missing. Yesterday when we were playing with Qiskit, that was sort of a free parameter. But I guess if you have a large qubit system, that's actually a gigantic amount of information. So is one actually practically never giving the state vector, just starting in ground state for all the qubits, or how does one handle that?
Okay. Yeah. So you mean when you have the design of the circuit? Yeah. So you assume that you are starting in a ground state? Yes. Yeah. And it's actually it's a nice question because it leads to one not so well-known fact, and that is it takes some time for the physical system to actually reach the ground state. And so what typically happens is that unless you have a fairly advanced system which allows to have an active reset, which sort of actively brings you to the ground state, what happens between runs of one user runs a circuit and then the next one, you actually have to wait in between to get the qubit relaxed to the ground state. And since you basically also want to like drive it tightly, you don't want to really wait for too long, right? You don't want to wait a few seconds. So you try to have it squeezed, which implies that not always everything has really relaxed to the ground state for the next run. So in practice, if you are an experimentalist, you have a full control over the system. But if you are a remote user, let's say of IBM system or HELMI or at Chalmers, you don't really have the control. So it may happen that not everything has relaxed as one would expect. Yes, please go on.
Yes, I would like to ask about the circuit on your last slide.
The very last.
The processing unit. If you could tell us something about the connectivity between the qubits, and if you could mention something about the, let's say, overall quality of the qubits, if you would compare it to, let's say, IBM quantum chips.
Okay, so the first half of the question, I think you're basically asking me to a little bit explain what you see here on the picture. Is that so?
Yes, or if you could describe a bit on how the connectivity between qubits look like, the possibility to do two qubit gates, for example.
Okay, good. Yeah. So these small crosses, I hope you can see my pointer. So those are the qubits. Then the thick red lines, those are couplers between these qubits. So this hopefully answers the question, like, what is the connectivity map? So that's these thick red lines between the small crosses. And the Hamiltonian we are using in the system leads naturally to either control Z coupling gate or I swap. And when it comes to quality, that's difficult, like for comparison with IBM, that's quite difficult to answer because we are developing this chip and we are right now in the third generation, and basically we measure, we figure out what doesn't work, then we improve the design, manufacture next chip, and sort of we are still in the process of basically getting it all to work. So we basically don't have the final numbers yet because we are still iterating the design, and also since, for example, IBM does not really have the same architecture, even the numbers, if I would have them, would not tell you, but it is like a first class quality. It is a top 10 in the world. It's in that range.
Thank you for the talk. In slide number 3, software stack.
That's somewhere very early on. This one?
We see that you put the pulse scheduler or something like that. Is it always pulse between control electronic and the compiler?
I see. Yeah, good question. So there are many quantum technologies which allow you to implement a qubit, more or less. Very much like any classical technology allows you to implement a computer. I mean, you can even build a computer out of billiard balls. It's just the clock frequency of building classical PC from billiard balls doesn't really scale well, and the controllability is also quite bad. So similarly in the quantum world, since we know that our world is quantum and some level, you can sort of you can choose any quantum mechanical system, and it will in principle give you a quantum computer. The only problem is that what sort of level of control you actually have over that system and how practical that is. So what we are using at Chalmers is something called superconducting circuits, and that's one of the most stable technologies there is for sort of like the control we can have. And the second big advantage of using superconducting circuit is that the manufacturing technology is largely identical to producing classical processors and microprocessors. It's really the same technology, just cooling it down to 10 millikelvins so that it's superconducting, and then we are in a different operating regime, but the manufacturing is the same. Yeah. Second, and there we are using microwave pulses as a level of control because it's electronic circuit. So what else would you do with the electronic circuits than actually send a microwave pulse to it? And then the second most advanced technology is something called ion traps, and those are controlled with microwave pulses as well. So basically, yes, we are using microwave pulses. It's what is used in most technologies which are that advanced as superconducting circuits, but there are tens of other different viable approaches, for example, like photonic-based systems. And I don't know exactly how they would describe their driving pulses. It probably also can still be tweaked as seeing a microwave pulse, but maybe they just use a different lingo for their control pulses. Yes, please go on.
So Chalmers has been designing its own QPU. So can you tell us a bit about your future roadmap?
Yeah. So the work we are doing on quantum technology is within this Wallenberg Center for Quantum Technology, which is a 12-year program sponsored by the Wallenberg Foundation. And our roadmap is going to slightly over 100 qubits, somewhere 120. That's our goal to reach in this 12 years. So right now we are in the middle of the program or the project. Yeah, we are in the sixth year, I think. And so right now we are finishing the sort of measuring the 25 qubit chip. We are starting design of 40. So that's the next step, which we should reach within the next few years. And the next step is 100, 120, depending how things go. Yeah, I should also maybe tell that there are other, so we are also involved in other European projects. For example, this Open SuperQ+, and that one has a much more aggressive roadmap. So for example, here in this Open SuperQ+, there is already a plan to deliver 100 qubits in about a year and a half or two. And then in 5-ish year, 4-ish years, having a reasonable roadmap towards 1,000 qubit. But yeah, so it depends a little bit also what kind of KPIs you focus on, because there is a really big difference in engineering, whether you focus on quality or just scaling up the chip. And both of these approaches have their own pros and cons. So yeah, it's not just, yeah, there are these two aspects, quality and quantity of qubits.
Question?
So for the chip you made, what sort of materials is it made of?
It's a classical silicon wafer with aluminium deposited on it. It's very much like any microprocessor, classical one. Yeah, no fancy materials. No, yeah, it's silicon aluminium all the way. There are more fancy materials which have slightly better properties, but you a little bit know that when you have to basically, when you are in the need of using very expensive materials in order to gain a 5% better fidelities, you know, yes, you are better, you may publish it, but it's not a scalable approach. Yeah.
Yep, sorry, one question. Well, we saw that you need some set of universal gates you can have a set of universal gates to express a circuit. So from the compiler to get into the pulse level, like, there are some pulses that define these sets of gates, and then you execute those pulses. And for example, I don't know if for example, a set of gates can be summarized in just one pulse. Does that considers those cases?
So is your question whether there is like a universal pulse?
No, what I meant is, like, I don't know, for example, if you have two sequences of gates, I don't know if it is possible in some cases, for example, that those sequences of two gates, even if are not, could be those basis gates, but then can be expressed as just one pulse, for example, that executes the same, or it's not possible.
Okay, so is your question whether there are multiple ways? So you have one logical gate, and you are asking whether there are multiple ways how to implement on the pulse level the same gate. Yes, that's absolutely possible, and that's a good question. I was thinking if I should discuss it while having this slide or not. So I will do it now. So when you implement a gate, depending on whether it's rotation around the z-axis or x-axis, or if it's coupling, that sort of addresses different parts of the Hamiltonian of the system. So Hamiltonian is some equation, and with some pulses, you can also little bit basically suppress certain parts of the Hamiltonians, because the Hamiltonian is there all the time, but you can, for example, suppress some parts so that only the Z or Rx or only the coupling part is happening. So that's one thing. And once you sort of do this suppression, for example, what we do is something called tunable couplers. So when we have a coupler between two qubits, you can actually tune out the frequency of the coupler to a regime where it almost appears like if the two qubits are disconnected. So there is a little of transfer of leakage information, which helps to like isolate. Good. Now it's getting too complicated. what I wanted to say is that the pulse you implement is just rotation in some space, and the angle of the rotation is proportional to energy you supply to it, and the energy is in turn proportional to the area of below the pulse. So more or less any pulse shape which has the right amount of area, meaning the right amount of energy, will do. And there basically comes a lot of optimization because, for example, let's say that if you look at these pulses, there are two basic parameters you can play with, and that is time and amplitude. Of course, you want to go like short in time because then you can execute faster, more pulses during your coherence time, but that implies that you have to go with high amplitude. But high amplitude means that you are driving your system like very strongly, and things are more likely to go wrong. You are basically applying too much power trying to be fast and driving hard. so there is a balance between time and amplitude. And then also the pulse shape itself sort of actually, it doesn't really have any effect from the, if you just calculate logically or solve the Hamiltonian equation, because it's just all about the energy. But in practice, the way it interacts with cables and connectors, the pulse shape actually also matters, like whether you choose a Gaussian pulse or a sinus pulse or something more fancy.
Speaker, Jake Muff, from VTT and CSC, or only VTT?
VTT,
VTT
CSC.
in Finland. So over to you, and tell us about HELMI. And remember now, I will post in HackMD as well as on Zoom where we are right now. So we are swapping 2 sessions.
Yes. Thank you very much. Yeah, so my name is Jake from VTT, and I'm a research scientist. I work with the HELMI, the quantum computer, and as you'll see later on, also the 20-qubit quantum computer that was just launched. So in this tutorial, this is more of a hands-on exercise, so I suggest that you launch onto the CSC Notebooks platform. If you haven't already done so, then you can post a message in HackMD, and someone will hopefully guide you with given access. There may be, I would suggest launching the session as soon as possible, because there may be some delay in actually launching the session. You should, if I would give just a quick overview, you should, once you've logged in, you should see some workspaces, and you should see some launch here, and once you click it, you'll get onto the Jupyter Notebook server. So in the essence of time, this picture here is HELMI. This is our lab in Micronova in Espoo, Finland. So right now, the goal of this notebook is to give an introduction to what HELMI is, and hopefully, if every one of you could run a job on an actual quantum computer, that would be a success, but we'll see. The notebook is quite long. I don't intend to go through all of it today. You have access to it for all of today and tomorrow if you want to go over any of the things we go through. And we will only be running some simple exercises today, but in principle, any of the things that the other instructors have taught you can also be applied to HELMI, given that it only has 5 qubits. Yes. Yeah. So this picture here, this is when we talked at HELMI and the actual lab. This is the picture of the lab. I think Miroslav described it quite well in the previous lecture, but here we just have the cryostat and the control electronics rack to the right, and then on the left you see some computer for controlling the cryostat and ensuring that we have millikelvin temperatures. So today, if we were physically, unfortunately you cannot be physically in the lab, but today if you had a live view, you'd be able to see the lights flashing on and off in the control electronics rack, hopefully. So to just begin with, this is just the introduction with Qiskit. You can also use Circ with HELMI, and for all of these circuits we'll be running on HELMI, as Miroslav also described, we have a very similar software stack architecture. So we have some sort of low-level queuing system. This is what Redis that Miroslav showed, and this means that you may see that when you're executing circuits on HELMI, you might not immediately be running, but hopefully when your turn is in the queue, you will be able to run your job. So as noted earlier, we're using the Qiskit framework to design our circuits, but also as this is an IQM and VTT co-developed quantum computer, they provided their own client libraries for accessing it, and this is what we'll be using today. And essentially, as it showed earlier, and if you're familiar with submitting to IBM quantum computers, we're pointing it at some sort of URL, which is giving us some information that we can send HTTP requests to, and that's where we'll be sending our circuits. So that's what we're doing here, is just setting up our back end, so to speak. And now that we have our back end, we can get some information, such as the native gate operations that you can run on HELMI, and what the coupling map looks like. And importantly, with the coupling map, this is what designates how you can make 2-qubit gates and single qubit gates on HELMI. And even though I just put a quick note here that it states that the native operations of HELMI are the rotation gate and the CZ, in principle, it's actually a phased RX gate. And then Qiskit doesn't have any such gate to describe a phased RX, so this is translated on the back end. And then this can be, you can display what the topology looks like. So here we see that it's got this star-shaped topology with qubit 3 in the center, and all the other qubits are the so-called outer qubits. Each connection between this designates a way you can make a 2-qubit gate between the qubits. So in this case, you can only really make 2-qubit gates between the central qubit, qubit 3, and any of the outer qubits. If you want to apply any circuit, you don't really need to worry so much about making this, because the transpiler will always insert swap gates. And then this is just an image to demonstrate that, perhaps, if you want to see it in a different light. But then, so if we just create a simple Bell circuit experiment that I think we saw yesterday, then we will be just run this on 2 qubits and hopefully entangling our qubits. But whether we're actually entangling them is another question. And then it's very simple just to run and execute a circuit. You can use this execute command, and you input the circuit and the back end and then the shots. And the shots is just the number of repetitions we'll be repeating it for. And then if we see this, then you get some form of unique job identifier. This can be used in principle if you say you want to run a job and then you want to go grab a coffee and come back to it. You can retrieve the job with the job ID later on. So if you want to, the results are stored on the back end, and this can really be used to keep track of what jobs you have submitted. And the only problem is you need to always remember to save your job ID. So now that it's actively running, you can always question the status. And I guess it's still running. So this might be a good demonstration of the fact that we have a queuing system. And so I'm also in this queuing system at the same time. And perhaps I can demonstrate how this is just a dashboard of what essentially is happening on the back end with our queuing system, which is why I'm waiting. I guess right now we have 11 jobs in the queue. So it might take a while to be able to actually execute my job on the quantum computer, but this just demonstrates how that you don't need to worry about having to book your time to submit jobs. You can just submit them, and then at some point you'll get your results back. So now the job is done. We can. Later on we'll get the results, but first off I wanted to explain that right now we did the most simplest way to execute the circuit. We basically gave it execute, and the Qiskit itself took care of transpiling it and routing it onto the decomposing the gates into its native gate set and routing the circuit. Importantly, now we can do something called explicit transpilation, which is using this transpile function. And this would actually show you what we're actually, we originally had this Hadamard gate and a C0. And when it's been decomposed into its native gates, we have a set of rotation gates and the CZ gate. Okay. So now now we've got, this is what, this is the circuit we just submitted onto HELMI, how it looks like. But say we wanted to, at the moment we didn't really get to pick our qubits, right? We ran here between qubit 3 and qubit 5, which is possible, yes, but we didn't really have a choice in that matter. So we wanted to run on either qubit 1 and qubit 3. We would have to choose this in what we call our qubit mapping. So here the trick is that Qiskit uses starts with 0 indexing, but the qubit numbers start with 1 indexing. So it can just always keep this in mind. But so here we just define that we map the first qubit in our register to qubit 1 and the second qubit in our register to qubit 3. So then, and then we can execute this circuit with the initial layout, and we can also double check that we've had the right mapping. And yes, we've mapped our first qubit in the register to qubit 1, and should be qubit 3. But importantly now, if we take the circuit and we print it, we would see that we'd actually run on between qubit 1 and qubit 3. And we can see our results that we get out by just plotting the histogram. And this would may also take some time to get the results. Hopefully not. Yeah. So now we see that when we have a Bell state, we're expecting either 0, 0 or 1, 1, which is what we get. But we also get some noise. And it seems like HELMI's in a... well, at least with these qubits, is in a pretty good state, given that we've only ran with 100 shots, but it seems to be working fairly well. And then we can, additionally, we can get some metadata about what job we actually submitted to HELMI, such that we get like the job ID. You can print the full actual, what we call the run request. So this is the actual, like Miroslav mentioned earlier, after it's been serialized into the JSON that's sent to the quantum computer. We can see what actual phase RX gates we get and what actual CZ gates with what phase. And this can be very useful for debugging, where if you got some strange result from the quantum computer, you can always double check what you actually sent, because as you saw with this translation, it might not be 100% clear what you're sending. And then we also have this what's called the calibration set ID, and this is every time we calibrate HELMI, we generate this set ID, and this is make sure that we can keep track of associating when you submit a job to what calibration set. You may be using an outdated calibration set, and by calibration I mean that the state, these quantum computers have to be constantly maintained and calibrated in order to execute these circuits. The qubits may drift in frequency, and we need to account for this by saving some settings. And then whenever you submit a circuit, you load these settings into the instruments, and this allows you to get the best results from your quantum computer. And then we can also see what physical mapping we use. And here we mapped qubit 1 to qubit 3. And of course, we can see what shots we ran, just to double check. And then another aspect is if you, not necessarily quantum computing time, I guess not right now, but it could be quite expensive in the future. So this is where these noise models and simulations come in. And we also have the ability to simulate our circuits with a local noise and using this fake backend. This is like similar to how IBM does it. We can have some backend where it has the same similar properties to HELMI, but you end up running on the simulator. And you can also, we'll see here, you can also add noise to the fake backend to see and match up with how realistic it is on HELMI. So for this, we use this fake Adonis. Adonis is the chip name that IQM gives for their 5-qubit chips. And you can see what kind of back error profile that is by default set. But we can adjust this error profile with some realistic settings for HELMI. So here I just took some simple case for qubit 1 and qubit 3, where I took some T1 and T2 times from earlier, and some depolarizing error rates, gate durations, and the readout errors. And we can now generate our fake backend, and we can execute our job. And once it runs, we can see how well we actually estimated our noise model. but I would guess that it might take a while. But at least people are submitting to HELMI right now, which is good. So whilst this runs, I'll just explain that you can also, if say you don't want to just submit one circuit to HELMI at once and you want to be more efficient with your time, you can also submit a batch of circuits. So say you wanted, and this is really for use case, as we'll find out later on, for parameterized circuits. Say you have some sort of angle you want to iterate over for a number of circuits. The circuit stays the same, but you want to change the angle. You can submit a list of circuits, and they would be counted as one job, but they're executed serially, which is best used for more efficient execution. We don't want to go constantly back and forth between your laptop and your quantum computer for each circuit, so you can just send a bunch of them all at once. And I guess the job is still executing, so hopefully no one is having any problems. And then the last state is that there is also the ability to use not just a Qiskit, but we also have the ability to use penny lane or and as well as Circ with HELMI, and this gives you different options with, say, if you want to do some quantum machine learning that penny lane, the software kit provides, then you could also run this with HELMI. And then we can see from our noise model, get it right, that we didn't do so bad, but it could definitely be improved. Again, we only ran with 1,000 shots. But this just shows that I think these parameters that I input for the noise model need to be tweaked on a regular basis if you want to achieve the highest accuracy. Of course, we don't use the noise model that much because HELMI is regularly available. But in the future, when larger chips become more scarce and more demand increases, then these noise models become very useful. And so now I've just demonstrating how to get a list of circuits. We just created this Bell pair circuit again, and instead now we just created another circuit, and we instead put the control X on the different control and target qubit. And then, importantly here, we've had to specify that the initial layout is, and this is an option into the transpiler to tell it which qubits to use initially. And this problem might be that, as I mentioned at the start, that your transpilation is stochastic in the routing, so in the sense that it may pick different qubits to run on. And when you do batch execution, one of the restrictions is that you must measure on the same qubits. So here we fixed that the qubits are always using qubit 1 and qubit 3 to make sure that we always measure on the same qubits in our list of circuits. So that was the brief introduction to HELMI, but I also had some, feel free to carry on submitting jobs. I also had some tasks to go through if you wanted to do some self-study, but I think we've got plenty of time. Importantly, they mostly for demonstrating Bell state on different qubits. Say you wanted to, you can use a Bell state to run, use this transpilation to run on different qubits and see which qubit pair is the best. And then later on, you could also entangle more than just 2 qubits, in theory, with a GHZ state, which has not yet been covered, and hopefully I'll explain. But let's first see if our batch execution is submitted, and it's still running.
Hi. So just one question regarding the queue that we place our jobs in.
Yeah.
Is it a global maximum length of the queue, or is it per user?
There is a global maximum length of the queue. At the moment, in theory, if we had each one of you, we gave you individual accounts onto, you have notebooks accounts, but not individual accounts on HELMI. We could also impose this per queue. But at the moment, we just want as many people to run on HELMI as possible. So it's just a global limit at the moment.
So at a later point, like a month or something, if you want to run on HELMI then, what would we still use the same method, or? we need to change?
If one wants to run on, so HELMI is outside of this school. Yeah. So HELMI is not is only available through LUMI at the moment, and perhaps I probably should have said at the start the original plan for this tutorial was to use LUMI and demonstrate some HPC-QC, but unfortunately LUMI has gone down for this week, so we've decided we thought it best to use the Jupyter Notebook server, and then at the moment HELMI is available for Finnish academics and researchers through LUMI, and the future plans will be to expand this to the Nordics as part of the Nordic project, which is why you're here, and then who knows what the future will hold. Maybe VTT is also part of this LumiQ project, although I'm not really a part of that. And in theory, HELMI could be widely accessible across Europe as well. Of course, then you get your more and more quantum computers are also popping up. So you won't just have a choice between HELMI or quantum computer in Finland, but Germany may have their own quantum computers, Czech Republic, for example.
And in case it's not clear to everyone who just heard this exchange, LUMI is the third largest supercomputer in the world, and it's actually hosted in Finland, in the north of Finland. And you can launch quantum jobs on HELMI from LUMI.
Yes. Yeah, and now we have almost 100 people running in the queue on HELMI. So I'll just quickly describe, whilst the jobs are submitted and run on HELMI, I'll quickly describe if you want to run some tasks on afterwards on HELMI, perhaps when it's quieter, maybe. So the idea with the first task was that as we saw earlier, we only ran between qubit 1 and qubit 3, but say you wanted to run Bell state between qubit 1, 3, 2, 3, or 3, 4, or 3, 5, which are your possibilities. How would you go about doing this? How would you specify your initial layout? And then I added some solution here. And then the other task was this GHZ state. And with this GHZ, this is where we are trying to entangle more than 2 qubits at a time. And in this case, with HELMI, we can really, well, in theory, we can entangle up to 5 qubits, although we'll see how successful this is, or you will see how successful this is.
There's a question here from Saul. How long is the execution supposed to take? It seems to take forever.
Yes, because everyone's the same problem I'm having is that there'll be a job running and there'll be finishing and then the next job. Unfortunately, with these with HELMI and quantum computers in general right now, jobs cannot be submitted in parallel. It's really one person first in first out type queue, which is why we're trying to keep in this tutorial anyway, the shot counts are very limited. Perhaps I can just describe the GHZ example. So with the GHZ, you saw that previously with Bell state, we created, we put Hadamard and a C0 just between 2. But now what if we increase this to all 5 qubits of HELMI? And this is more like, this example here is almost the textbook example of how to create GHZ. And we see that with the simulator, what we're aiming to get is all 0s or all 1s. This is only 1,000 qubit, 1,000 shots. But then you can immediately see that the transpilation took longer because we have more qubits, but more the circuit length has exploded compared to what we had previously. And this is just because if noting that how the topology of HELMI has a star-shaped topology, you can see how if we with this circuit and knowing that qubit 3 is the only one that can have 2 qubit gates, we're going to have to include some swaps. And so Qiskit will automatically include these swap gates, which leads to this lengthening of the circuit. And as noted, the more gates you include in your circuit, the more error you accumulate. And your goal is to really what's called error suppression. We mentioned error mitigation, error suppression earlier. But with error suppression, we're trying to reduce our number of gates or our depth of our circuit. When I talk about depth, I'm talking about the total length, how deep, how many gates single qubit and 2 qubit gates in your circuit, and the more of these gates you have, the more errors you will accumulate, especially when the single qubit gates we're achieving fidelities at the moment, industry standard of 3/9 of fidelity, 99 and 3/9, which is pretty good, but a 2 qubit gate fidelity is really the limiting factor with these NISQ devices. So these swap gates are 2 qubit gates that we try and implement, and as we add more of them, we're increasing our noise. So now I want to demonstrate. So this was when I talked about adding a swap gate. This is what you can automatically, instead of putting the back end in here, you can just put the coupling map, and this will route the circuit, but it won't decompose any of your gates. So now we just see what the routing of the circuit is, and we've seen that we've implemented some a swap gate in here, and it's also mapped it automatically to qubit 4. So now, if I skip ahead, now we can see if we create a more somehow hardware-aware GHZ state by manually creating the circuit so that's on qubit on the central qubit. So now our GHZ state looks different. We're using it all on qubit 3, and this will reduce our depth and minimize the number of swap gates needed. So now you can see the circuit depth is much lower, and if I would demonstrate right now, but I'd probably be stuck in the queue again, that this job will also have a much higher success rate, or the plot will look much similar to the simulator. Yeah, and at least the jobs are being submitted slowly. But it's good. This is exactly what I intended, because now everyone's actually being able to run on a quantum computer. So, and then later on in this notebook, I also demonstrate some simple readout error mitigation that Mikael described earlier. And this is really to improve the results from our NISQ devices. If you believe me, I'll try and describe what it would show if it was running on HELMI. It would be the GHZ state is a much more complicated circuit compared to it, and so the results would be not matching the simulator really at all. It'd be very noisy. It'd be lots of not just all zeros and all ones. There'd be some in between. And really, with this readout error mitigation, you can improve your results. But instead, now that the queue on HELMI is so long, I can probably pivot to showing the other quantum computer, a VTT. So recently, and this is not officially part of the schedule, because Finland's 20 qubit quantum computer only just was launched a few weeks ago, and so I just came up with this quick notebook, and you can also I'll put this in the shared folder, and you can also try this later on. But Lena is our 20 qubit quantum computer. Is also co-developed by VTT and IQM, and it has 20 qubits and 30 couplers. So this is the lab. Previously you just saw the HELMI from this picture, but now you see in our lab Micronova we actually have 2 cryostats, the bigger and the smaller one. As with the number of qubits scaling up, the infrastructure needed also expands quite rapidly, and the lab is quite crowded now. So yeah, and then so luckily I ran this earlier, so you can see. I'll need to zoom out a bit. Hopefully that's fine. So the topology of the 20 qubit chip is also much more complicated, but you can now see that we can create not just this star-shaped topology, but we have this lattice-shaped structure, so you can have even more couplers enabled. And this is also allows you to sort of pick your qubits much better. You're not just limited by running some 2 qubit gates between a central qubit, but say that qubit is not acting so good today. You can go and shift to another qubit. So let me just run this. So now I will. So supposedly, pretend earlier we ran our GHZ5 state, and now we want to run a larger circuit. So previously, yeah, we were limited by 5 qubits, but what if we try 7 qubits? Now, I'm not saying that this will show any quantum advantage, but at least give you a picture of what NISQ devices are like currently. So immediately, yeah, we have the same familiar circuit as before, just with 7 qubits this time. But immediately, perhaps if I run this again, you can see that the transpilation takes not too long, but I guess probably an order of magnitude longer than with 5 qubits. Especially, and now that the circuit is, yeah, incredibly long, and it also increases, it adds all your qubits. So now, if we execute this job, with the HELMI and LENA have separate queues, so in principle I should not have to wait at all. But of course, when you talk about scaling up your number of qubits, the time it takes, even your initial offset for submitting a job also increases, just because matter of fact you've got more instruments and more overhead in actually executing your computation. But here we see, okay, so we managed to submit to LENA, and in this case, if, for example, one of the problems I will demonstrate here is that if I don't limit this by 3, the plot becomes quite unfeasible to even view. So that's why I always try and limit this to 3. And you can see that we're getting a lot of all our 0 states, but all our 1 states are out. And this is because if we can take a look at which qubits we're actually using here, it may be difficult to describe, but you can see that we're running on some qubit. Remember, it's offset by 1, so qubit 15, 16, 17, and making some 2-qubit gate between them. Now, I know this is expected, but you guys might not, so perhaps there's a reason for this, and that is because the calibration of quantum computer is really precise, and you can only calibrate when you 5 qubits is I want my co-workers might not like this, but it's relatively trivial to calibrate 5 qubits compared to 20 qubits when you have you not only do you have 4 times as many qubits, but you also have 30 couplers to also calibrate and make sure that you're not influencing each other's qubits with crosstalk effects. So here you can see that there's a reason why we said we ran on qubits 17, 18, and 19. And this is a recent, let me see if I can zoom out. This is a recent calibration of LENA from, I think, yesterday. And you can see that qubit 19 is not even coupled at all to the other qubits. And this is because we explicitly made a choice in this demonstration to decouple qubit 19 in essence to boost the fidelities of the other qubits. So it's expected that in this case we would not get that good result because our transpilation automatically transpiled to qubit 19. So now it's gone off the screen here a little bit, but now we can improve our transpilation by providing this initial layout. Now here I've done the thinking beforehand, but we know that we want to create a 2-qubit state. So I picked the 3. If I could draw a line, it would be 3, 4, 1, and then 2, 5, 6, and 11. And so we're saying, okay, we want to keep away from these bad qubits. We want to go and shift to the good qubits here. So then we execute this. The transpilation takes probably just as long, but you notice that we're not there. The bottom half of the circuit here is empty. It doesn't have any gates. This is what we're looking for. And we also have all the 2-qubit gates are mostly towards the bottom right end of the topology. We can see here, but this also noted that I also printed here that it comes at the expense of the depth. So the Qiskit transpiler is it's an optimization problem. It's trying to route your circuit you give it onto the topology and reduce the number of total gates. So here we have a depth of 21. So Qiskit thinks this is good because it's reduced the total number of gates you submit in, but obviously it's not aware of the current state of the system. So when we provided this initial layout, the length of the circuit increased to 36, but in principle we've avoided the so-called bad qubits. And then if we run this result and wait for it to run, we should, in principle, see an improved result upon the other one, because we are not trying to even drive qubits which cannot be driven or can be driven with such a quite a low fidelity.
Questions here from the online audience. So one is revisiting HELMI, and the question is, what is the probability for one-shot 5-qubit entanglement?
One shot. I wouldn't be able to do the maths off the top of my head, but you wouldn't. Running with one shot would make almost no sense, because you really need to have some. You need to be confident in your result, and this is why we do repetitions to increase our entanglement. But the question of are our qubits actually entangled is something that I'm not really covered at all in this lecture, and this requires much more in-depth about, there's a good Qiskit tutorial on it, about entanglement verification. You'd have to do some state tomography, and really to make sure that your qubits are entangled. But in this tutorial, I'm not saying that my qubits are entangled, I'm just showing that what kind of circuit would entangle them.
And one more question here on Lena. What is the accepted depth or gate length?
So both Lena and HELMI don't really have any restrictions on the depth of the circuit. From our findings, the depth of the circuit doesn't really affect. It affects the result for sure, but it doesn't affect the time. And so it really makes no. There's this IQM in their software has this good flag which tells you basically if you submit a circuit to HELMI where the circuit depth is much longer than the relaxation time of your qubits, then it makes no sense to carry on the computation. So this is what you're really looking out for: is the how deep is my circuit versus what is the T1 and T2 time of my qubits, because this essentially is the T1 and T2 time is how long our qubits are actually coherent, and then how long it takes them to then relax. So yeah, so now we ran, and let's, if we can compare. So now we got, I would say this is not such a good result. Like our highest state is not all zeros, and the all one state is not even present on the histogram. So if actually I did some quick, where is it? Yeah, so you can do some quick like probability estimation. We got like only 944 counts were even all zeros or all ones. So this is out of 10,000 shots. This is not great. But if we then have a look at this one, we've now got about 1,700. So you can already see how just by picking your qubits and manipulating your transpilation, you can drastically improve your result. But there's one other trick, and that is I've sort of, when I did this initial layout, I'm telling Transpire that I know more than you, and you should only use these qubits, but it's only limited to these qubits. Now, what if we just remove the bad qubits altogether? We say don't even completely ignore this in the transpilation. So this is what this cell is here doing. It was saying, okay, we've got qubit 19, 9, and 7. Remember, it's 0 indexing. So we just want to remove them from our coupling map. So now our graph looks much different. We've got some qubits which are completely on their own, but this is fine. And then so our transpiled circuit now Qiskit is we've let Qiskit pick the qubits, but only pick the qubits which we've told it to pick, essentially. So it was still now it's explored the options and optimized the gate depth, and now we've got even the gate depth circuit of 21. So we've improved. We've got back to our roughly the same as we had originally, but we've ignored the previous qubits. So now, And I ran this earlier, and you can already see that we're getting about 3,700 out of 10,000 shots, which again is another improvement upon the result. I guess the key takeaway here is that if when you move to larger qubits with much more complex topology, you really need to start thinking about which qubits to run on and what pre-plan your algorithms. It's never with these sort of NISQ devices, you cannot really throw your circuit at it and expect the transpiler to work some magic. You really need to be somehow hardware aware, and this is perhaps the main limitation of these NISQ devices. Okay, so somehow this didn't work, but I guess I'm glad I ran it earlier because it did work. Again, this demonstrates how the transpilation is stochastic, and the current calibration of lane might have degraded since I ran this last night. And this is also quite a common problem, is that we have to recalibrate our machines quite regularly. But yeah, and then I guess people are still running on HELMI, which is good. And I don't have anything more, so any questions?
One more question here from Ricky. So does qubit fidelity change like daily? Does that mean one would have to update the program frequently to rerun efficiently on the best qubits?
Yeah, so the qubit fidelity, so we don't have that much information. The 20 qubit is relatively new, so we don't have that much information on how that behaves over time. With the 5 qubit, the single qubit fidelity is relatively stable. Like we know we can keep about 2 nymphs or 3 nymphs of fidelity. That's fine. But it's the 2 qubit fidelity which is the trickiest part, and this is because of these superconducting qubit technology. We have these couplers which are really tricky to. We want somehow to. We call this find the idling point, where we want to know we can actually drive our 2 qubit gate without influencing our outer qubits. And this because if you move away from this idling point, then you may may accidentally start driving another qubit, or the hardware starts becoming trickier to read out. And then the other problem is that the readout fidelity of these qubits is also not with HELMI it's quite stable, but the current with the current industry with this readout fidelity is a big issue. Trying to be able to correctly read out your qubits as best as possible is the one of the big problems to overcome.
But one fun question maybe before we break up, which is, does HELMI mean anything, or is it just a fun name?
Yeah, so HELMI is actually means pearl in Finnish, and I guess this was the name because it's Finland's pearl. It's small but precious. So that's the meaning behind it.
Small and precious. Miroslav will show us a hands-on example, a challenge that people can work on this afternoon. I think you will introduce it for half an hour, and then after that we switch over to the next QAOA session here with Franz.
Okay, good. Thank you. Yes, you can hear me. I can hear myself as well. So, welcome back after lunch. So my plan right now is to basically bring you yet closer to the hardware and tell you a little bit about the pulses and also how it interacts with the chip. And so my plan is more or less just, I originally thought that I would just leave I will leave you to read this through, and then you do the small exercise with analyzing the data. But then I understood that it might actually be more advantageous if I accompany the text by explaining a little bit, because you can read it afterwards. Good. So what you see here is a real picture of one of our older chips. I think this was about 5 qubit size. And the reason why I included here is just to give you the scale of how the chip sort of looks like in the real life. So one important thing to notice here is that it's not really small. People are often sort of assuming that, as we are in the quantum regime, that somehow these qubits are also like a super tiny molecular kind of size. These superconducting circuits, actually, they are not. They are even much bigger than classical CPU transistors, like 1,000 times bigger. So it's definitely a microscopic object. So that's why this picture. And then if we look under the lid, there's a photo of the chip itself. So this is a chip from one of our PhD students. he's working on, I should also emphasize that at Chalmers, even though our main goal is to get to this roughly 120 qubit chip, we are actually also developing multiple smaller chips with different designs, sort of experimenting on the readout part, experimenting on the coupler part, experimenting on fast adiabatic gate. So we are actually having multiple cryostats and multiple different chips and exploring multiple different paths. So this is one of our experimental design. So not all chips look like this. This is one particular design. And there are multiple components which I would like you to notice. So to start with the simple stuff, these are feed lines. So this is where from the microwave pulse is either coming into the circuit or coming out of the circuit. Yeah, so feed line. All these small lines, that's a grounding. That's one thing which is a little bit unusual, because from classical world, you sort of know that if you want to ground something, it's good enough to do with one cable. This is too sensitive to just have it with one cable. So what you are doing here is that really trying to have the same ground everywhere, because if you do it more sparsely, you would actually end up with something called ground loops, meaning that you actually have multiple different grounds with a small different voltage. So yeah, all these tiny hair-like wires are actually there for grounding. Good. Then these circle guys, these buttons, those are the qubit themselves. Yeah, these qubits, they typically what you see here, basically what is the visible part, that's a capacitor part. So when you have the qubits, we are using two main electrical components, and that is a capacitance and inductance. So in some super simplified way, our circuits are quite ordinary LC oscillators with a small change that ordinary inductive element is a linear component, but we need a non-linear component. I will gloss over why. And therefore we use something called the Josephson junction, which is typically marked like that. But for your memory, it is just a non-linear inductive element. Yeah, and there is no resistor because we are working in a superconducting regime. So all of our circuits are exclusively just a parallel and in sequence connected inductive and capacitive elements, no resistors. Yes? This is probably like 2 centimeters by 1 centimeter, something of that order. Yes. Good. And so this is the circuit diagram of a chip, just basically by components. And then the physical way how it actually looks like is fairly often quite different. So one of the most common type is to use these cross-like elements. And this is just a big capacitor with this particular shape. The reason why we are often using these cross-like shapes is that then it's easy to have a coupler around it, which physically looks something like this. In this particular design, the decision has been the guy who decided, Anush. He decided to go with a circle design of this capacitor, so he's basically having some sort of this structure. It doesn't really matter because the capacitance is proportional to the area of the element. So the shape, the geometric shape, is just a secondary option, or depending on what you want to do and for what reasons. But it's the area of the capacitance which matters. Good. So those are the qubits. These lines are couplers between them. And these wiggly lines, those are readout resonators. And that covers it all. So for example, if I just start here, this is a feed line which controls the qubit state. This is a feed line which controls the coupler state. And this is a line which is connected to the readout resonators. And these readout resonators, or the line which is the readout line, which is here, is typically multiplex. So we typically read more than one qubit at the same time. So this readout line is multiplexed. All right. So with this real picture, I will now go more to symbolic sketches to make it more tangible, yeah, or more easier to understand. So I will just draw one qubit with one readout resonator. So this line, here we go with the readout pulse. Here is a readout resonator. And it is connected, let's say, to this cross-like qubit. It doesn't really matter the geometry of shape. It's all about, when it comes to readout resonator, the resonator frequency is proportional to the length, so it's the length which matters. And here is the area of the capacitor which matters. Good. And now, when we manufacture this circuit and we want to use it for the first time, we have done some specific design choices, basically what kind of resonance frequency this resonator should have and what kind of resonance frequency this qubit should have. The reason why we sort of want to have different frequency for all the components is that there is always a lot of crosstalk in electronics. So by addressing different components on different frequencies, we try to isolate that basically the pulse reaches only and only to the component. There is still always a leakage, but by sort of working with that each qubit has slightly different frequency, it's easier for us to address them individually and minimize the leakage. Good, so both the frequency of this resonator and the working frequency of this qubit has been designed somehow, but after it's manufactured, we don't know exactly what is the value, because it's one thing to sort of simulate this in some simulator, but the moment you manufacture it, you cannot really somehow see it. The only thing you can do is actually send a pulse through it and make an educated guess based on what kind of measurements you do, how it really worked out, how well we have manufactured, how it performs. So what we do is that we need to start with measuring the readout frequency of the resonator, because if we cannot read out, then we cannot even really get to the qubit nicely. So we send so-called readout pulse, and this pulse is typically of a square nature. Doesn't really matter why. It's more convenient for this particular purpose. And what happens is that depending on frequency of this pulse, a part of the energy just passes through, and part of the energy is going into the resonator. And the closer, so we are basically sweeping different frequencies coming in. So at first we send a pulse in some frequency F1, then we send pulse, okay, so there is some wiggly line in here. Then we send another pulse with slightly higher frequency. And then one more pulse with even higher frequency. And we are measuring the pulse responses at the outcome. And what is happening is what you can see on the screen here. And so these are the different frequencies we are trying. The blue dots are the actual measurements, and this is the voltage which is measured here on the output. And so you see that if we are far from the actual resonance frequency, much of the voltage is not going into the resonator, it's just passing through. So we don't have much losses. And the moment we are approaching the right frequency, more and more energy sort of gets sucked into the resonator, and little is sort of passed through. So that means that we are measuring small amount of voltage on the output. So by doing this sweeping of the frequencies, we get these measurement points, and then we do a fit. And based on the fit, because also most of the time it doesn't look so nice. Depending on sort of how things go, there are usually qubits which are better, and the actual measurement may look like this. And then there are qubits which are worst, something went a little bit wrong in the manufacturing, or there are other influences, and then it actually doesn't look so nicely. So that's why the fit, which is kind of trivial in this case, sort of is not always so trivial. Good. So with this simple experiment, by sweeping different frequencies, we are able to, after doing the fit, we are able to determine what is the resonance frequency of the resonator. Good. And then there is one interesting fact, and that is, since this resonator is coupled to the qubit, the state of the qubit, whether it's in 0 or 1, actually influences the resonance frequency of the resonator. So its frequency changes depending on the state of the qubit. And that is this yellow line. So in case the qubit itself has some energy in it, there is some complex physics behind it. These two elements are coupled, and this leads to this frequency shift, which is quite smart, because if you notice, if we say that, okay, we should always do the readout on this specific frequency, then if on outcome we measure this, I don't know, this 0.6 probably millivolts, or no, it's in volts, then we know the qubit was in 0. And if we happen to read out something like a 0, 16, 18, then we know that the qubit actually was excited, it was in state 1. So depending on this difference on measured voltage on this readout line, we are basically able to infer what was the state of the qubit. Good. So now we know what is this readout part and how it helps us to determine what the state qubit actually was in. And it's also good to know that there is a term for this sort of measurement called a non-destructive measurement. It is a little bit unfortunate term, because you should know by now that when you measure quantum state, it collapses to one of these classical things, one of the classical outcomes. So there is this collapse, which is quite difficult to motivate or explain, but yeah, there are some rules in quantum mechanics. But this non-destructive measurement somehow implies as if the superposition is not really destroyed. That's not the case. So what this non-destructive measurement means is just that we are not measuring directly on the qubit. We are doing indirect measurement on the readout resonator. So if you somewhere see a term called non-destructive measurement, the thing still collapses. It just means that it's an indirect measurement through some other element. All right. So with this knowledge, we can now try to also measure the frequency of the qubit. All right. No, this is all right. Good. Good. So here is another line, feed line, which is coupled to the qubit itself, and that allows me to send pulses directly to the qubit. So this readout line was directly connected to the readout resonator, and then I have a dedicated line for the qubit control. So I can do basically something fairly similar. So I will be sending pulses, this time not square pulses, but some Gaussian or cosine pulses. And I can again change the frequency, so I can have some slow frequency pulse, and then I try the same pulse shape with a higher frequency and an even higher. I think you get the picture. Basically, very much think as I did here, and then let's just see what happens. So, what do you think can happen? So, when we are sending this energy in, it sort of again depends whether the frequency matches with the frequency of this capacitor, because at some frequencies the energy will either be reflected, so sort of like not going into the circuit, and in some other frequencies the energy will go in. And maybe by now you already start to see or guess what will happen, and that is, if we are off the frequency, if we are just sending pulses which are completely far away, then everything just gets reflected back and we don't really care about it, meaning that the qubit has not consumed energy, meaning that it did not went from ground state to the excited state, meaning that this is what we still read on the readout line. So the voltage stayed quite low because the qubit is in a ground state. And then we continue sweeping the frequencies, so sending higher and higher frequencies pulses to the qubit. And at some point, we will start observing increased voltage here. And that's exactly because we are approaching resonance frequency of the qubit, meaning that the qubit actually is able to swallow the energy. So it's basically getting more and more closer to the one state. And as I have shown you before, the resonance frequency of the resonator changes with the state of the qubit, meaning that the moment the qubit is excited, I will be reading out a higher voltage. So this is what is visible on these plots. That I'm sweeping, and at some point it will go up. And then I know, then I do the fit again, and then okay, so this is my frequency of the qubit. So anytime I want to talk to this qubit, I should basically do it on this particular frequency. Yeah. And I guess now we also are getting some sort of picture how big the problem with leakage is. Because you see that even if I'm slightly off the main frequency, it still leaks. The qubits still get excited. It's really only when I'm far away that it doesn't work. So there is always some sort of crosstalk which is very difficult to isolate. Yeah, and that was all what I wanted to tell you. And now what you can do is that somewhere here is a link to our website, cal9000.se. Okay, it's here. And from there, you can actually request a piece of this spectroscopy sweep of the qubit, and then using the code which is provided here. Yeah, there is some code. You can actually do the fitting yourself, and you can look sort of how the data look in the real life. And with that, basically, the way this spectroscopy data, the raw measurement, has been acquired. Basically, we have prepared and still measuring a few hundreds, maybe even 1,000 of these spectroscopy data. And each measurement is basically unique because we are also measuring across multiple qubits. And then we chunk it up, and then we repeat the measurement over and over. And since this is a real physics, real analog device on this level of pulses, basically each measured data is really unique. So it can be said that when you apply to receive this spectroscopy data, the raw log file, you have somehow received a fingerprint from the real device, which is at Chalmers. So it's not just 0 and 1s, as you, for example, got with HELMI after doing some Qiskit circuit. Here you are getting a real fingerprint from the real physical device. All right, I think that was all what I wanted to tell you. So feel free to download from our web page your oven piece of data. If it for some reason doesn't work, we have also pre-stored one file on GitHub. So there is one pre-stored file which you can also do a week later or whatever when you like. And now I can do questions. Yes.
The voltages that you're measuring. I mean, you're doing microwave pulses in. So is it RMS voltages that you're measuring out during the application of the pulse, or?
Sorry, one more time.
In principle, your output voltage should also be oscillating with the frequency of the input microwave.
That's correct.
So the voltage that you're showing here, just the scalar, is that the RMS voltage response, or?
Yes.
Okay.
Yes.
Hi. Can you go up a little bit? We can use that picture. Now you have explained how the single qubit measurement or operation is. So can you use that picture to show us that, for example, how we entangle different qubits, 2 qubits entangle each other, or multi-qubit entangle each other? How the hardware can really do that? Now you explain how we do in 1 qubit. So. Thank you.
Yes. Yeah. That's actually what it was on my slide during the software stack lecture. So I will try to open this file again here and navigate to the right slide. Where is it? It's here. Yes. Good. I think this is good enough. So here, okay, it's better for the online audience if I use my pointer here. Good, it's visible. So here, if we ignore this U1 gates, the single qubit stuff, you are mostly asking how do you do the entanglement gate, right? That's this controlled X in this small circuit. So you see that I'm actually sending multiple pulses on different lines. So this coupler is connected to this drive line called U0. So I'm actually sending these complex pulses here. And then also there is a pulse accompanied on the drive line 1 as well. So you are sending pulses to multiple drive lines with the right alignment. Okay, I see. So the quantum entanglement is a form of correlation. It's not so you need to apply some physical action to achieve this correlation, but after entanglement is established, it's just a particular form of correlation. So you should not think about as there is some, let's say, some physical wire between the two qubits after that. That's not the case. Probably the right way how to think about it is, let's say, marriage. So in order to get married, you need a partner. You preferably get to the same place so that somebody can come with a pulse in the form of a diploma saying you two are married now. With that paper, you have received your certificate, you are correlated. You can now go apart. Whether you sort of one of the couple lives in Austria and the other one in Germany or France doesn't really matter because the correlation by the certificate is still there. So you had to put some energy to basically make it happen, but after that you only have this notion of a correlation. And that's quite similar what is happening here. So there is no some hidden binding thread entanglement. It's just a correlation, very much like being married. Yeah. And actually this analogy worked quite nicely because if one of these partners decides to be unfaithful, the correlation sort of stops working, but it's only one partner that actually knows. The other partner still think that it's fairly undermined, which is exactly what's happening in this EPR experiment where you entangle two photons, send them far apart. And this is exactly what basically Einstein called the spooky action in distance. That is that you entangle two photons, send them far apart, you collapse one, and ever since that you collapse the one on either, let's say, horizontally or vertically polarized, it predetermines the state of this one immediately. But this guy doesn't know. And it's the same thing as when you sort of break your marriage certificate by cheating because only one party which did the measurement knows. The other one does not know yet. You either basically have to use classical information to tell him or her that it's over. So classical information, no instant action. Or the other option is that the second party also decides to take a measurement, and then it knows as well what the outcome is. Yeah, sorry if this becomes unusual.
Hello. So, kind of. So the physical quantity that is quantized in the qubit system is then the frequency at which that circuit can oscillate.
Yes, you can say so. It's quite yes. So what we are quantizing is energy in the circuit. Yes. So we are when I mentioned that we have this nonlinear inductive element, that's a reason why, because if you have linear inductive element, then the energy space or the energy levels in the circuit are equally distance spaced. So by inserting this carefully crafted nonlinearity, we are isolating the ground state and the first excited states as a computational space. And this energy is coupled to the frequency. So it is correct to say that we are quantizing energy and we are containing the state of the qubit between being in a superposition of ground state and the first excited state. And nothing else can ever happen.
Okay, thank you.
Going back to your comment on multiplexing and frequency scales. So you show there that you had one readout line for multiple qubits. So how do you achieve multiplexing? By separating in frequency? Could you comment on that? And could you comment on readout frequencies versus the transition frequencies of the qubits? Which one needs to be larger or smaller to prevent crosstalk?
Okay, no, I'm sorry. This is I'm largely a software person, so this goes outside of what I can confidently talk about. But one thing I can try to explain is that. Okay, is it okay if I erase this? Okay, maybe it's. I can start anew. Good. So. This is in, here is out, and here it goes into the circuit. And we are sending some pulse in. And we are measuring some pulse response out. Difficult to say exactly how the measured pulse response out look like. And now the thing is that we are actually not looking actively at this very shape of the pulse response, because that's too complicated. It's too wiggly, too complicated to really understand why the shape looks exactly like this. So what we do instead, because also as I mentioned, the voltage sort of changes. So depending on how things turn out, this sort of might go higher or lower. So with that, we have basically figured out that it's enough to look at the area below this pulse. Because by looking at this area, effectively integrating under this pulse, we can infer whether it should be 0 or 1. Yeah, and then one way how to do some trivial multiplexing would be sort of to, yeah, I don't want to get into multiplexing. I don't understand it enough. Yeah, but there is this notion of integrating, and from this area you infer whether this region corresponds, this amount of region corresponds more likely to 0 or 1. Yeah, and actually it's also visible in here. So, okay, I will try to move this slide a little bit down. So. This is the readout pulse itself. This is what's going into on the readout resonator. So this is the readout pulse on channel measurement 0, and this AO, that stands for acquisition. So this is actually a signal which is going to the classical electronics, telling when it should start doing the integration process. So this is actually not a pulse which is not going to the fridge. This is an instruction for the electronics to start integrating. Okay. I have one more thing which maybe I can tell you at this point, but I don't know if there are more questions. Yeah. So when Mikael discussed his talk, he a couple of times mentioned that there is an unprecision in readout, and I can tell you one more thing where from some part of the unprecision actually comes from, and with that I will stop talking. So when we are. When we are sending in these pulses, we are actually not sending just one pulse in per drive line. We are sending in 2 pulses because we are using something called IQ modulation. Yeah, those of you who have some background in telecom, you probably know that whenever you want to transfer information through signals, there's always some modulation involved. That's basically how you modulate the signal to added some meaning to it. And there is one particular popular modulation called IQ, where you actually have two signals which are shifted by 90 degrees. And that's also, so they are 90 shifted. And that's also why people often call them convenient like a complex signal. Because these two signals sort of hang together, they make sense only together. And since they are shifted by 90 degrees, it's basically okay to call them a complex signal. And that's also what is visible here on this slide. So the reason why these two pulses are in different color actually means that one of them is in the I plane and the one is in the Q plane. Yeah, so we are actually having not one pulse per drive line, it's two pulses because of this IQ modulation. And then when we do this integration under the readout pulse, this area, we effectively get out two numbers because we have two pulses, meaning two areas. And we can draw this in this IQ plane. And if I do this, I will get a point in the IQ plane, right? And let's say that I'm just starting, I'm preparing my qubit in state 0, and I basically just prepare the qubit, I let it be in a ground state, and then I measure, nothing else. I just measure after ground state, and yeah, there will still be some pulse response, some imprecision, I will get a number, and or two numbers for two areas, and I will get a point in IQ plane. Now, if I repeat this experiment, I will never really hit the same point twice. I will get a cloud point. Right? Yeah, I mean there is always some imprecision. It's never the same thing twice. So if I just let my qubit be in a ground state and I measure, I will receive this cloud point. Now, if I excite my qubit and do the same experiment, so I excite to the first excited state, number 1. And then measure, I will start receiving another points, but I should do it in the same color because that's sort of, you don't really have colors when you measure, you just get numbers. So I will get another cloud point which will easily look something like this. And now you are hopefully starting to see a problem, that there is a problem of so-called readout state classification. Because if things are really good and you manage to design your system very well with these separated frequencies and things are good isolated, you sort of really get you get two clouds which are easy to tell apart. Or you get two clouds where it's actually not so easy to tell them apart. In practice, these clouds will always somehow overlap. That these are data coming from measurement number 1, or state 1, and these are data coming from 0, and they will typically overlap. And it's basically up to you how big statistic you sort of collect and how good you do this state classification. So this is one more source of readout error where you sort of have to classify the raw numbers, these IQ components, and turn them into classified 0 or classified 1. Yeah, if you do this experiment on a small chip with just 2 qubits, you can easily have a separation which is like this. If you are on a crowded chip, this becomes much bigger problem. Also, some people like to throw machine learning in this example. Sometimes it helps, sometimes it does not. It depends. All right. Thank you for your attention, and have fun running the small code, finding the peak of doing the fitting curve.
Thank you very much.
Everyone hear me now? Perfect. So this is an introduction to QAOA. I will say QAOA because it's easier to say. I won't stumble upon it. It's intended to be for someone who has some mathematical background, maybe physics background. Linear algebra should be sort of the basics you should have. But it's intended for someone who hasn't seen QAOA before. So if there are any questions, please just raise your hand, and I think we should take it interactively. I'm not sure if that's allowed, but I would actually prefer it. So before I start, I introduce some notation. In quantum physics, in this part, you typically use this Dirac notation, or also called Bra-Ket notation. And this is a common notation for quantum states. For me as a mathematician, it took some getting used to it. And in the beginning, I thought, why do they do it so complicated? But then after some time, you actually appreciate this notation more and more. So when you're not used to this, then as you have this bra and the cat actually you can just think of it as a vector in. Yes, I can point on the screen. It actually just denotes a vector in a vector space. So just think of it as a vector. And the bra is, you can think of it as the transposed vector, which can also be looked upon as like a linear functional, which is an element of the dual of the vector space, to be very mathematical here. And you can identify these with each other. So you can always make a linear functional out of a vector by just associating this as a function. When you have a Bra-Ket, so a bracket, then this actually denotes an inner product. So it maps the two vectors, or a bra and a cat, into a complex number. And if you do the opposite, if you do a cat bra, then this is the outer product. So the first one, the inner product, is a scalar value, a complex number. The outer product is a matrix. Yes, so quickly again, quantum bit, so just that we're on the same page here. So a quantum bit describes a state in a two-dimensional vector space, Hilbert space, and it's always a unit vector. And this can be described by an orthonormal basis. Typically you use this computational basis state where you denote this cat 0 as just the vector 1, 0, and the cat 1 as the 0, 1. So it's just the normal basis that you're used to from linear algebra. And you call it the computational basis state. Since it's a normalized vector, you have these complex numbers A0, A1, which have to sum up the square to 1. So this is the typical setting for one qubit. And in contrast to classical mechanics, here you can actually have superposition of states. And a typical, or just a random example, is that you have even with complex numbers, and you have this combination, but the sum of them has to sum up to 1 if you take the absolute value squared. Multiple qubits then basically come for free. You just tensor your qubit Hilbert space n times, and then you have n qubits. And here you also have different bases. One of them is the computational basis, which can be written in many ways. And they're all equivalent. So you have 2 to the power of n basis states. And you can either just enumerate them from 0 to 2n minus 1, or you can write them as binary digits. So 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on, up to 1, 1, 1, 1. This is equivalent. This is basically a lazy version of writing the tensor product between all these states. And as a vector, it just has a 1 at the digit that is indicated by this here. The general state of a one qubit can be written as the linear combination of all the basis states with complex factors in front, which again have to this square. The sum of the squares has to be 1, so it's a normalized state. So there's a remark. So this is a 2 to n dimensional space because you need 2 to the power of n basis elements to describe it. And classical bits, you have only has dimension n only, because you basically specify each point is a 0, 1, so you only have n degrees of freedom. Yes, so quickly, what is a product state? So if I give you a state phi, then if you can write it as the tensor product of individual qubits, then we call it a basis state, otherwise it's called an entangled state. So a typical product state is this one, which you can take, write as exactly the superposition states, 0 plus 1, tensor product 0 plus 1. An entangled state is this Bell state, which you have prepared where you take the Hadamard gate and then a controlled knot, then you get this state, 0, 0 plus 1, 1. And this is not a product state because you can't write it as a tensor product of two individual states. Yes, I think I skipped this one. Quickly, operations. When you do operation on a quantum computer, you do your computational way. Then you apply these gates, which are unitary matrices. I wrote down the definition of what it is. It's a self-adjoint operator. The kind of the reason why it is like this is because if you apply it to a unit vector, then you still get a unit vector. Or it's not the reason, but it's why it makes sense. Exactly. So all operations are linear and they are all reversible. I guess you've done this before, so you have this sort of standard gates, the Hadamard gate, the Pauli X, Y, Z gates, some phase shift gates, and you can even have like square root of knot gates, which are basic rotations in the Hilbert space. And another thing that you probably have seen many times now is the controlled knot gate, which I wrote down in matrix form and as a circuit. And it takes the second qubit, flips the second qubit if the first qubit is 1. And you can do also a controlled unitary gates more generally. So now we have to go to what is the variational principle. And in order to talk about this, we have to talk about what are observables. So observables are self-adjoint operators in the Hilbert space. And from the spectral theorem, we know that a matrix H, which is self-adjoint in finite dimensional setting, there exists an orthogonal basis, phi I, with eigenvectors that are all real. And then you can write this H, your self-adjoint operator or your observable, as the sum of the eigenvalues times this projections onto this subspace. So it took me a while to understand why physicists call these energies, but these eigenvalues of such an operator are called energies, and they're all real, as I said, and they can be ordered from smallest to largest, and they actually amount to certain definitive energies the system can have. So that's why they're called energies. And then to each eigenvalue you have an eigenvector. And these eigenvectors are called eigenstates. And since they're ordered, you can call the one associated with the smallest eigenvalue as a ground state. And then you go the first excited state, second excited state, and so on. This is kind of a quick and dirty look on how you can imagine this, but I think it still gives you some intuition. So the ground state is if an electron sits like on the innermost shell, and then if you excited one more, one shell up, then this is kind of the first excited state. Do you tell me when we should take a break? Okay, perfect. So what are expectation values? Then you're given a state, which you prepare with a circuit, for instance, on a quantum computer, and then you're given a certain observable that you want to get the expectation value of. And this is just defined as this term here. But we can go further and use this, what I showed you on the slide here, that H can be written as the projection onto the onto the subspaces times lambda I. And if we plug this in into this equation, then you can see then you can take the sum and the lambda I outside, and then you can get this term here. And in particular, this means that if you prepare a certain state, which is an eigenvector, or a what's it called, an eigenstate of the system, then you actually get exactly the right amount of energy that you measure. So this physically makes sense. In general, you will have a superposition of a general state is a sum, weighted sum of your in the spaces given by h. So this psi I, and then you in this expectation value here, then you get how much it overlaps with the certain subspaces. And now we can go to the variation in principle, which is fairly straightforward. So this is from the last slide, the expectation value of h when you take the state phi is given by this. But it's very easy to, in the sum, to just take the smallest eigenvalue. So this is a lower bound. But since so that you can take this outside of the sum, and since these are probabilities, they should sum to 1. So the whole expression is bounded from below by the smallest eigenvalue, or the ground state energy. And this gives us a general way to compute something on a quantum computer using this variation in principle. So if you can find a way to encode your problem as the ground state of such an observable, or this Hamiltonian H, observable H, then you can try to prepare a parameterized state, and you can try to find the optimal parameters such that you minimize the expectation value, which you know is bounded from below by the smallest eigenvalue. So this is the variation in principle. If you want to have like a pictorial view of this, then the blue line, the blue circle here is supposed to be the full Hilbert space. Your ansatz, which is the way you parameterize the state, is basically the green circle. You don't reach, maybe not reach the full state, but only a subspace of full Hilbert space. And then when you optimize these parameters, you might use, for instance, a gradient descent method, and then you go, at least ideally, you would go within the space to your solution from an initial state. And the overall overview of this hybrid quantum classical solvers, whatever the problem is, you can you should formulate it as a Hamiltonian, where the ground state corresponds to your solution. You prepare a trial state, you measure it on the quantum device. Then the classical device calculates the cost function, or the expectation value, and you update these control parameters until you hopefully reach a good solution. One thing that I will not talk about, I think this will come later, is quantum chemistry problems, which are maybe the most natural candidates for this. So imagine that you have two hydrogen atoms, and you can change how far they are apart. And this will give you this potential energy profile here, where at some point it's minimal, they bind, and then if you try to squeeze them closer together, then it will have a very high energy. I'm not a physicist, so if I say something wrong. And if they're too far apart, they will not feel each other. So you get this typical profile here. And then you can write this down as a Hamiltonian in second quantized form using the Born-Oppenheimer approximation and so on. But this is not really a part of this presentation or lecture. But I just wanted to mention that this is one standard example application for this variation in principle. The thing I'm going to talk about is combinatorial optimization problems, particularly the max cut problem. And I guess some people have seen this before, but I will quickly try to describe it. So here in this setting, you're given a graph which consists of vertices. So in this picture, it's the 1, 0, 1, 2, 0, 3, 4 circles, and you have edges between them. And they can even have weights attached to this. So for instance, between 0 and 4, there's an edge with the weight 2, but there's no edge between 1 and 4. And then you try to find a subset S, or you try to partition these vertices into two sets, S and not S, and this defines a cost function for you. Because what you do is that you basically go through, given such a partition of the vertices, you go through all edges and you see if they are in different sets. Then you count this as a cut, and then you count this as this weight of the cost function is added. And if they're in the same set, then you don't add it. And this mathematically can be written down like this. So you assign to each vertex the value -1 or +1. And you can see that if they're in the same, then for the edge ij, this is 0, and if they're different, then it's omega ij. And you want to maximize this. And this is an NP-hard problem. Just a quick example here. So if we, for instance, have this partitioning, so in red and green sets, to make it very graphical, then we can go through all the edges, and the dashed lines here are the ones that are cut. So this would have the cost 4. So I think it's natural to maybe take the break now.
How long are we taking a break for? We could take a 15-minute break now and then take another break later this afternoon.
Yes.
Maybe. Yeah.
Between lecture and hands-on.
We could do that, yeah.
Yes.
So let's take 15 minutes until, well, just a short sort of leg stretcher until 10 minutes past the hour.
Perfect.
There's one question. Shall we take
it
quickly?
Okay, I can take it.
Any real-world applications of MaxCut?
I think there are real-world applications. I've talked to some practitioners, but I couldn't tell you. I think it's more real-world if you use the max K cut. So this is the max 2 cut, where you only have 2 sets. But if you have K sets, then it becomes very quickly more applied.
All right. Okay, so let's take a break. Everyone, welcome back from coffee break. There was a question that came up during the coffee break, which I will now forward to Franz. What is the difference between QAOA and VQE that you also mentioned?
Yes, so that's a very good question. So both of them are hybrid quantum classical algorithms, and both fall into this category of variational algorithms. So the difference is QAOA is specific to optimization problems, and VQE is specific to quantum chemistry problems. And the type of Hamiltonian you get in optimization problems is called a spin Hamiltonian, which basically means it's a diagonal matrix. And VQE doesn't have this type of Hamiltonian. It's more complex, and you have many non-commuting terms in the Hamiltonian. So I hope this answered the question. Let's go back to QAOA with a max cut problem. So we start with the smallest case possible. That's always a good idea when you want to learn something. And the smallest non-trivial example of a graph is one with 2 vertices and 1 edge. I mean, the more trivial would be just 1 vertex, but that's too trivial. We want to have at least 1 edge. And then we're going to encode the information of if we're in set S or not S as in the qubit as the ground state or the excited state. So 0, 1. So if we're going to have 2 qubits and the states will be 0, 0, 0, 1, 1, 0, 1, 1, which encodes the information that they're in the same set or in opposite sets. Then you have this Pauli set matrix, and I hope you remember that if you apply it to the zero state, so the zero state is a +1 eigenvector of the Pauli set, and the one state is a -1 eigenstate of the Pauli set. That means that when you apply it to 0, you don't pick up a phase, and when you apply it to 1, you pick up a phase. And then you can define this Hamiltonian, so it's or an observable set, which has exactly this characteristic that if you pick up no phase, so if it's in the 0 state, you pick up no phase, or in the 1 state, it picks up two phases, which becomes -1 times -1 equals +1. This is then the excited state, and the ground states are the one where you have a difference in the states. So they're in different sets. And with this intuition, we can go to the max cut for a general graph. And as a reminder, I've put here the cost function, which was given as this term. So whenever you are in different sets, you add the weight of the edge, and if they're in the same set, then you don't have this weight. And then it's fairly straightforward to encode it in this form, because for every xi, you just put a Pauli set gate. And then you can, with this intuition from the last slide, you can see that this adds phases when they are in the same, when they're in opposite phases. So it gives you a lower state, lower energy when you have different states. So different sets. Yes. So in general, what you can do is if you have a QAOA, a quadratic unconstrained binary optimization problem, which can be written in this form. So you have, that's why it's called quadratic, because you have most quadratic terms. And you want to minimize this. So find the bit string x that gives you the minimal value of this term. Then this can be straightforwardly transformed to an Ising type Hamiltonian by basically making this transformation for each xi. You replace it by identity minus the Pauli set matrix. So there are more than the max cut example, but in this we are going to only talk about the max cut. One thing which gives you a nice intuition is something called the adiabatic theorem. And this states that a physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough, and if there's a gap between the eigenvalue and the rest of the Hamiltonian spectrum. So I'm trying to explain this. So in this setting, you have a time-dependent Hamiltonian. So this Hamiltonian h depends on the time t, and you have certain other parameters a and alpha. Then you can calculate the eigenvalues, which are the expression is given here, but you can see the plots here for certain values. And you can see that if a equals 0, then these lines actually meet. So there's no gap between. And if a is positive, then there's a gap. So the eigenvalues at no point in time meet. And this this theorem basically says that the probability of a transition of going from one state to another state is given by this expression here. And you can see that this probability is 1 if a equals 0, because e to the power of 0 is 1. So this is kind of the cornerstone of what, for instance, D-Wave does with the quantum annealer. So it's a very physical way of trying to kind of go to the ground state of a Hamiltonian. So in this quantum annealing, typically you have a schedule where you, in time t equals 0, you start with a certain Hamiltonian, where the ground state is easy to prepare. And then you anneal, you change slowly your Hamiltonian over time until you reach another Hamiltonian where the ground state is encoded, the solution is encoded in the ground state. But the ground state is really hard to guess or to just prepare. So this is a way to prepare the ground state by kind of physically going there. It turns out that the runtime of this algorithm, typically it depends on this minimal gap, the size of the minimal gap. So it's order of 1 over minimal gap squared. So that means if the minimal gap is really small, you have to go really slow in order not to go to an excited state. Yes, so the minimal gap, if you're in the ground state, is the distance to the next eigenvalue. And it turns also out that this minimal gap can be shown to be exponentially small with respect to the problem size for hard instances in MaxCut. So annealing ultimately doesn't solve NP-hard problems, which is probably good, as we have heard before in another lecture. Otherwise, everything would collapse and we could solve basically everything in a way. Here's another example, which is maybe more towards the MaxCut application. So our target Hamiltonian is the set where we know the ground state is the excited state because that has a minus phase. And our initial Hamiltonian is the minus x, where the ground state is the plus state, so the uniform superposition. You can plot the eigenvalues of this, and you can see there's no minimal gap. But what is maybe more interesting, because for 1 qubit, and that's why I used this small example, you can actually plot the Bloch sphere, which I hope you've seen before. So this is kind of geometrical representation of a qubit. And if you prepare the plus state, if you start in the plus state, then if you anneal, then the instantaneous eigenstate takes a path towards the +1 state. And if you start in the only other state, in the minus state, you go to so in the first excited state, you go to the first excited state of your target Hamiltonian. Are there any questions? Good. So here again, I wrote down the weighted MaxCut as a Hamiltonian. Okay.
QAOA solves
yes.
min of x to the power, let's see now, x to the power of t, equation.
Yes.
Can it also solve for max? Or max bx plus c?
So I'm not quite sure I understood the question. So it solves the minimum, it tries to minimize this whole expression, but you can actually, the c doesn't matter, so you can get rid of it. Yeah. And the b, since x is a binary vector, can be just absorbed into matrix A in the diagonal.
I think the main gist of this question is whether it can solve maximize, I guess, if you just invert the whole thing and take the minimum of it.
Yeah, I mean, yeah. If you take a minus, then you maximize. Yes. So it's... Yes. But you have to be careful. For instance, the max cut is NP hard, but the minimum cut is not. So yeah, there are some pitfalls. Yeah. So for the max cut, you have this kind of target Hamiltonian, which we know the ground state is our minimizes or maximizes, depending on the sign, the cuts. And then you have to choose, so this is a diagonal term with a number of edges terms, which is nice. And then you have the kind of the starting Hamiltonian, which you typically choose to be the X Hamiltonian. So it's just a sum of X Pauli matrices. And so you know that this has only off-diagonal entries. And this HB, the role of it is that it swaps operations between neighboring qubits. So, but we're going to see a slightly better picture of this quickly, very soon. So how do we find... So now we don't want to do this annealing, but we want to have a digitized version of this. So we want to approximate this, this kind of schedule by doing it on a digital quantum computer. And then we need to quickly go through how when we exponentiate matrices, and if they don't commute, then this is not equal. So e to the power of h1 plus h2 is not equal to the product of the exponentials. It's only true if they commute. Luckily, there is something called a trotterization, where you can show that you can still do it, but you have a certain error. And there are also there's this first order version and higher order versions of this. So you can still trotterize, but you have to be aware that you introduce an error. And then the overall QAOA is that you have this layered approach. So you have P layers. In the depth 1, you first apply a unitary that is associated with your problem, and then you do this mixer Hamiltonian. I've written down these terms here, and since all the HB terms are just X terms, they all commute. So this is actually exactly this, exactly this form, and this means you don't introduce a trotter error here, and you can do the rotational X gates all in parallel. For the Hamiltonian that is associated with the problem, it's a diagonal term. They're all diagonal terms, only Pauli set terms. And also this can be done exactly. But between them, you have a trotter error. If you take e to the power of minus I beta HB plus HC, it's not equal to the product of these two matrices. But that's fine. So we obtain this expectation value when we prepare the state, and then we can measure the expectation value. So this is more a calculation. Maybe I can actually just give you the gist of this, and if you want to look in the details, you can do it afterwards. The slides are online. So what you do in practice is that you measure it over and over. It gives you a bit string. You can calculate the cost of each bit string just by the classical cost function, which is very cheap. And then you get the probability, you multiply it by the probability that you got the string. So if you get a string 001 20 times out of 1,000 times, then the probability it's 20 over 1,000 times the cost, and you continue like this. So it's very straightforward to calculate. Then if you want to actually implement this, you can write it as these basic building blocks, which don't have a trotter error. And you can show that you can, this exponential here of the Z gate is exactly this C0, a rotational Z gate, and a C0 again. And this can also, if you want to convince yourself, you can actually do the hand calculation. It's just small matrices, so it should be fine to do this by hand. And this is also a good exercise if you're a bit unsure about like tensor products and these kind of things. It's a very good exercise to get into this. So now we know how to implement the phase separating Hamiltonian or the cost Hamiltonian with gates, and it's even easier for the mixer because each of these terms is just a rotational X gate. If you want to somehow get an idea of what the X mixer does, this is maybe a bit overwhelming in the beginning, but just look at one of the terms. So for instance, these blue terms is the X1, and then the next one is the X3 and the X4 and then the X2. So what these rotations do, and they rotate in the subspaces. So you can see with the errors that when you do the x1 term, it kind of operates on the first qubit. So it rotates from this 1, 0, 0 to the 0, 0, 0. So in the superposition, you can rotate in this subspaces. So that's kind of the role of the X mixer. It can guide you towards where the solution is. If you only had the phase separating, then you would not change any expectation value, and you would only get a uniform superposition of all solutions. So when you have NP-hard problems, then there are certain types of approaches. First of all, just brute forcing it takes an exponential time. You can probably see that there are 2 to the power of n bit strings, and that takes exponential time with respect to the size of the problem. There are certain heuristic algorithms. They don't have a polynomial runtime guarantee, but they appear to perform well on the instances you want to have them work well. So they're quite popular, but QAOA is an approximate algorithm. So it's an efficient algorithm which provides provable guarantees. In order to see what I mean with provable guarantees, there's this thing called an approximation ratio. So basically it says how far you are between the best and the worst solution. And when you're very close, it assigns the value 1. If you're completely off, then it applies the value 0. So this is just depending on if you maximize or minimize, it changes slightly this formula. And but yeah, so this approximation ratio for a probabilistic algorithm says that with a very high probability, we get a solution that has a certain is equal to or larger than a certain approximation ratio. And in order to give you some intuition what QAOA does, I took this example graph here. It has, I don't know, 10, 12, 14 vertices. So it's not very large, but it serves as a nice illustration. If you would randomly sample, you take a random bit string and you sample from this, you would sample from this distribution. So the approximation ratio would be 9 point something divided by 14.2 or something. With this standard deviation, which is this gray area here. So you would not get a very good solution because the tails here, if you want to maximize the tail, is very few optimal solutions or close to optimal solutions you have. So what QAOA does is it changes this distribution. So I can just, it has this depth, and now I will go through the different depths, and you can see that if you have higher and higher depth, then this distribution it's very likely you will sample very good solutions. So this is kind of, it's still a stochastic approach, so you still need to sample and sample, but the distribution is, if it works, is a very good distribution because you sample from the good part of the solution space. So overall, what you do is you have your original problem, which might be discrete, and you actually transfer it into a continuous optimization problem, a global continuous optimization problem. And you can discuss if this is a good idea or not. But this is the overall approach. Discrete problem, like maxcut, on a graph is transferred to finding the minimum. So you want to find this parameters such that the cost is minimal. This is only a 2D plot, but for higher depth, you have 2 to the power of 2 times the depth variables. So it's a very high dimensional space, and you have to have very good approaches for finding the global minima, because you might get, very likely you might get stuck in local minima, which are far from optimal. Yes, so I think it's time for the hands-on lecture to to do some interesting things. I think it might even be interesting for people who have done QAOA before, because hopefully. But there will be a prize for the best solution. We'll talk about what defines this. I wanted to buy Norwegian chocolate, but I somehow forgot. So this is Danish, but this is probably also good. So this will be the prize. Yeah, I think it's your turn. So thank you very much. But if there are questions, then we can probably take it now.
Questions here from our online participants. So
good.
The first one is there a quantum algorithm for solving binary optimization problems with inequality constraints?
Yes, I mean there are certain approaches. It's easier with equality constraints, and there are different types of approaches. So one of them is that for inequality, you can introduce slack variables, which means you need more and more qubits, and then you can add it irrespective of its if it's inequality or equality constraint. You can add this as a penalization term. But this approach is fairly hard to get to work. In theory, it's nice. In practice, it's quite hard, and we've actually struggled a bit with this. There are also, in certain settings, you can design these certain mixes. So if you start in a feasible subspace, so only the subspace where you have feasible solutions, you can guarantee that the mixer doesn't get out of this subspace. So there are approaches, but they all have their pros and cons, and they might or might not be applicable for the specific setting.
And there's one more question. When considering this combinatorial problem, or these problems, how many qubits are necessary to solve a problem with the decision variables? And then clarification, in the case of max cut, I would want to know what vertices are in what set.
I'm not quite sure I understand this question.
Well, you can have a look maybe in the HackMD document later and give an answer by text.
So you need 1 qubit per vertex, but I'm not sure if that was the question.
Okay.
Yes. Yes.
Yeah.
Yes.
Yeah. I'm trying to wrap my head around your parameters per layer. Could you go back when you did the trotterization of the UB, UC?
Just say stop.
You had a long product of
this
these operators. Yes. So each and one of these are parameterized by a component gamma and beta.
Yes.
So naively, when we worked with the gates before, we could only introduce phases, which are sort of bound between 0 and pi. But are these, should I think of these as angle variables or actually unconstrained real variables?
Yes. So first of all, there's a small mistake. There should be a gamma. But yeah, so there's kind of the intuition. These are all rotational gates. So there's no doubt about that they rotate in certain subspaces, but this is only giving you phases, not global phases, but local phases, and this one is actually changing where you are in the full Hilbert space. I'm not sure if that answered your question.
So is gamma and beta unconstrained, or are they constrained?
They are in principle unconstrained, yes. But for certain problems, you can have symmetries. And when you plot this landscape, then typically you have to be very sure how you scale it, because you want to look into the right part of the landscape. So it might be that, okay, maybe I can do this quickly. Is there a way to erase this? There. Oops. So when you do this e to the power of minus hc, which is such a large diagonal matrix, then you can if you order it with and you have a beta or gamma here, so you have a e to the power of minus I gamma lambda 1 to the e minus gamma lambda max. So that's max min if we order them. Then you can see that with the gamma you can sort of see how much you rotate in the space. And if gamma with respect to lambda, so lambda min and lambda max goes too quickly, then you kind of skip over a lot of details. So you want to somehow make sure that you scan this, you do this rotation once for the largest rotation. Yes. Okay.
So, okay, you can hear me now. Okay, so now we start the session of the hands-on on the MathCAD problem. So we're gonna repeat again all the introduction about this. To open a little bit, yeah. So we're gonna restart introducing the cost function and the definition of the problem for the MathCAD problem, and we're gonna deal with many type of let's say mixers and ways of express this problem during the notebook. But okay, so as I said before by Franz, this type of problem we have a graph with vertices v and edges e, and some weight between the different nodes of this graph. The MathCAD problem is in this case we have only two partitions of the sets, so we can represent our different partitions with binary variables for each node. In this case, I wrote down differently from before, as Franz has done, the cost function in terms of the binary variables xi, xj, where xi, xj takes values 0 and 1. So in this case, I'm summing on all the edges and all the nodes of the graph with different weights wij, and the cost function takes the terms xi1 minus xj. Before it was slightly different because he was assigned the variables to values -1 and +1. Yep, sure. So, starting, this is our cost function. The idea of the MathCAD problem is to try to find the binary string that maximizes this cost function. So, from the computational point of view, this is an NP-hard problem that where we have like many type of approximation solution that can work in polynomial time with a guarantee approximation ratio of 0.8785. So the first thing that we want to do is to generate a graph to work with. So the first two cells are generating a graph. For example, in this case, we can generate a graph of dimension 8, for example. And here we have a graph. This is the first graph that we want to try to solve. So the first thing that I ask to you is like you to build a cost function that takes in input the graph G that is constructed with network X and a string, and returns me the value of the string and due to this graph. So I should leave you some time to do this, or I should deal with it? I don't know. It's should be with all the other notebooks. It's called MathCAD CAS 2033.
It's been shared in the notebook. The link to it has been shared in HackMD at the very bottom. It's in the Zoom chat as well. So if you go to this episode of the training material, under day 2, tutorial quantum alternating operator ansatz.
So I'll leave you some time to do this, but actually what we have to do is to try to implement exactly this function here for a generic string with the weights wij. And in this case, the generate graph in the cell is just an unweighted graph. So we have like all the weights at value 1. So this is a really easy to solve case, let's say, respect to the most generic one. But here we want just to understand how this mechanisms work. Yeah, maybe. Someone has done it? Was able to find a way to encode this string? Yeah.
I'm just thinking aloud. So get the matrix from the graph, multiply left and right with the x vector and the not x.
That's a way, but it could be hardly difficult to do that, because the A matrix in this case, in the full, it's a 2 power of n times 2 power of n matrix, because it should map bit string to bit string. So you can do this actually just going through the edges of the graph. Every time that you pick an edge, you have to do the sum in the calculation, because the sum here goes through the edges, to the vertices, not to the edges. So scales with a number of nodes. I want just to return you the cost function, so a scalar value that is related to the cost function. Yeah. Well, maybe I'll show the code. I don't know. The thing is, like, we want to calculate this cost function in a polynomial time, non-exponential time. So, like, to allocate the whole matrix, that is hard, because you have to allocate the values for each bit string. Should contain, well, string contains 0 and 1s. So I want you to calculate, but I give you one string of 0 and 1s and bit strings, not one and bit string, and I want you to calculate the cost function related to that string given the graph from before. Yeah. It's a one solution of the problem that will have a cost, but will not be the best one. But this is necessary for later, because we want to optimize this function, and we will measure many bit strings. And each time that we measure, we want to know which is the value associated to that string. So it's for later. Select the rows of the matrix. The matrix, you mean the edge matrix, like? The weight matrix. It's still like... yeah, it's like, mostly is the formula. The thing is, like, if you look at this, at the formula, you will have two possible values for each term, or wij or 0. It depends only on the string that I get to. Yeah, we can go there. Maybe it's time to try to understand how it works. So this is the solution, for example. So what we need to do is go through the edges of our graph, and for each edge will correspond to the bit of our n-bit string I and j. And if they are different, then the term will contribute to the cost function. So if the string I is different from the string j, then I sum to c the weight associated to that edge. And I will try to explain. But this is like scales with the number of edges that is not exponentially, as like, for example, all the bit strings values. So I just, for each edge, I check if the bit related to that edge are equal or different. And if you are different, then in this term here, they will contribute with Wij. So I just sum the weight related to that edge to the cost function and return C. Yeah, no. I said it's not exponential as before because he was suggesting to allocate the whole values. So once we have the cost, this cost function that returns me the cost function related to the string, and given the problem G, what I want to think about is like how I map this problem on a quantum computer. Yep. Yeah. Yeah, it's there. Okay, I let you do that. Sorry. Wij, and you got xi, that's what you meant. But the thing is, like, if you look at the sum here, you got xi, let's suppose it's 0, 1. When you go through the sum, I is 0, j is 1. In that case, the contribution is 0, but when you go with the other one, so you go through ji, you will obtain again ij. Yeah, it's another way of writing it down. Yeah. But it's the same. Mm-hmm. Yeah. You want to? I mean, there are many ways. This was mine, but the. It's like it's. You mean it's redundant?
So what you mean is that you would like to have an I and a j here?
No, if you go up, you get the weight from the edge. In initialization, you looked over the edges of the graph.
Yeah, you could do that.
Yeah. Okay, so the thing is, like, now we need to map this cost function in an Hamiltonian, a phase Hamiltonian, as was explained before by Franz. So to do so, what we want to do is like to map the binary variables to the spin variables. So in this case, we need a transformation, and this transformation is this one. So for each binary variable xi, we associate the spin variable 1 minus sigma x over 2, where sigma x is the Pauli matrix z. So applying this transformation to the previous cost function, what we obtain is this phase Hamiltonian here, where there is a rescale weight w tilde with a minus wij over 4. So once we have this Hamiltonian here, what we're looking at this problem, like, it looks like a spin model in physics with like some random, typically weights wij. What we want to find is the ground state of this Hamiltonian here. So which is the minimum eigenvalue and eigenvector, because we are interested in the eigenvector, so which are the partition of this of the max cut. And to do so, as stated before, we need to be able to implement the exponential of the single terms that compose this Hamiltonian HP. And the single terms in this specific case of the max cut are just exponentials of the z operator, so z tensor z. So in the second part, in this second cell, what I want you to do is to implement in the function of theta is just a parameter, will be our parameter in our algorithm. I want you to implement, which is the quantum gate that represents the exponential of z times z. And because this will be the building block for our algorithm later. So as we will expect, is a 2-qubit operator because it's z times z. So in Qiskit, they can down like using the initializing a quantum register with 2 qubits, and then we will need to apply some gates to our quantum circuit. The question is, which are the gates? That was shown before. Yeah. So as stated, we have that. We are interested in implementing the exponential of this type of operator here. So 1, 0, 0, minus 1 tensor product with itself. So performing this tensor product, what we obtain is this matrix. Sorry. It's a diagonal matrix, as we expect. And we have like the value is minus 1 for state 0, 1, and 1, 0. And it's plus 1 if they have the same spin, so 0, 0, and 1, 1. What we want to implement is the exponential for a generic parameter theta of this operator here. And we want to implement it using the gates natively implemented in the quantum computer. So the circuit will look like this. We will have two registers, Q0 and Q1. I'm writing really badly. Sorry. Yeah. We will have two qubits, Q1 and Q0, and then we need to apply a CNOT gate and a rotation gate with some parameter theta, and then another CNOT. Now, with this circuit, the exponential of this matrix, how will look like? Will look like the exponential of this matrix here. So we will have that this matrix will look e to the power of theta, e to the minus power of theta. So this is our building block, this operator here. So it can be implemented using two CNOT gates and one rotation Z. So I want you just to write it down using the Qiskit framework. And this should be easy, I hope. Yeah. So as we see, just we need to apply the CNOT gates from the quantum register 0, so from the qubit 0 to the qubit 1, then the rotation with the theta parameter on the second qubit, so the qubit 1, and then again the CNOT gate. So now that we have our Hamiltonian, the probable Hamiltonian that encodes the cost function and our building blocks, so our exponential of the double Z rotations, double Z gate, what we need to do is trying to implement the ansatz of the QAOA. And the ansatz of the QAOA is composed, as said before, by p layers of alternating two gates. The first gate is the exponential that we want to implement. And the second gate is the circuit UM that I need to point with the with the mouse. And the UM, for the case of the unconstrained problem, so this is an example of unconstrained problem because we can take every possible bit string as a solution. We can use the exponential of the sigma x gates. But to start with, let's construct the Hamiltonian circuit. So now that we have, now that we have all the single double Z gates and their exponentials, what I want you to do is like, if I give you the graph, so the problem, can you implement the exponential of the problem Hamiltonian? So, in other words, what I want you to implement is, we know that our problem Hamiltonian looks like the sum of Wij, Zi, Zj. And the phase circuit, UP, looks like e to the minus I gamma HP. So the important thing here is like we have to implement the exponential of a sum. And as I stated before, if the operator doesn't commute, we have to be careful. But here, every operator is diagonal, so they commute. So this operator can be wrote down as the product on Wij of e to the minus I gamma Zi Zj. So taking this in mind, this is the circuit we have to implement. Yeah, here. Wij, but here, for this problem, it's 1. Exactly. So we have like, it's n qubits, so we'll have many pairs will have this coupling. Yeah. We do like QC append, and here we got the ZZ gate with a parameter theta, that is the parameter in the cell, applied to a list containing the register we want to apply. So in this case, for example, will be QRJ. And this is something that in Qiskit used to be like this. You can define personal gates, in this case, and append it to lists of register qubits. So I show you how to construct it. You were looking for something? Okay. So to construct the circuit, as we said, we have to go through all the edges because we have to apply for each weight Wij the exponential of gamma Wij ZZ. So what we need to do is just rescale properly, because as we see before, there is a rescaling factor of 4 in the cost function. So for each weight, we append for the Z gate with the weight Wij rescaled times the cost parameter, because here we want the parameter there to be multiplied by the weight, and apply to the nodes I and J. So we need, it's very similar to the structure of the weight, the cost string, but instead of like calculating the cost, we apply the gate. So once we do this, this is how the circuit looks like, for example, for an 8-qubit problem. So here, for example, we have, this is the structure of the exponential of the ZZ gate, and here is applied, for example, between qubit 0 and 1, 0 and 2, 0 and 3, 0 and 4, and so on. So it's really a simple circuit that can be, of course, optimized in terms of depth, because here, as we see, most of these gates, in some sense, commute, so we can choose a nice order to reduce the depth of the circuit. But here is not the main topic. It's about the QAOA. Yep. As I said, it's like you go through the edges, take the nodes relative to that particular edge, and extrapolate the weight. In this case, it's trivial; it's just 1, and then you multiply the weight by the cost parameter divided by 4, because the 4 factor is just due to the transformation of the classic cost function to the quantum one, and then we need to multiply by the cost parameter that will be used during the optimization. So going on, the thing is like now we can implement this class. You don't have to do nothing here. Just put your way to calculate the cost function and to create the cost circuit. And the other thing that we need to do in this max-cut problem is to be able to define the proper mixer gate. So as I stated before, it's like in this case we have an unconstrained problem. So one of the the simplest mixer that we can build is like this HM mixer, where this Hamiltonian looks just as the sum of the sigma x operators here. So these are the Pauli strings with 0 and 1. So here before, in this case, the operator, the cost function looks like this, but the mixer where the sum is on the qubits. And the sigma x is this operator that does not commute with the z operator. So it's just the Pauli string. And one important thing here is like that the sigma x and the sigma z times sigma z operator, they don't commute. So the thing is like how, in terms of basis gates, implement the exponential of the mixer Hamiltonian. And here again, this Hamiltonian is composed just by sum of single sigma x terms. So this is really simple, because the first thing is like they commute, but not only they commute, but they act independently on each gate. So it can be wrote down in this way. Because we can just deconstruct this sum by the product on I of the product of the single terms. But they act directly on different spaces because they act on the different qubits. So this is what we need to implement in this new cell. The exponential of the mixer with only one parameter, the beta, sorry. So just copy paste the solution. Yeah. So as we can see, just we need to go through all the qubits in our system. In this case, we have the number of qubits is of course the number of nodes of our graph, and apply the Rx rotation with the free mixer parameter here called beta, and apply it for each qubit. So I just Okay, in fact, the circuit is really simple in this case. We have just one X operation for each qubit. So in this case, the depth is 1, and we don't have CNOT gates. So the other choice that we have to deal with in the QAOA algorithm is the preparation of the initial state. So we have found a way to encode the cost function. We choose the mixer that we want to use for this optimization. Now we have to choose which is our initial state, because, as we said before, the QAOA ansatz psi, they represent our wave function. So our way to describe the ground state of this Hamiltonian depends on a vector of parameter gamma and a vector of parameter beta, where gamma is related to the cost and beta to the mixer, of p layers of alternating the mixer term and the cost term applied to initial state. The thing is like, who we should choose as an initial state psi 0 for our algorithm. And as I was described before, this QAOA algorithm is inspired by the quantum annealing. So the idea is to start from the ground state of the mixing Hamiltonian. So the mixing Hamiltonian looks like the sum of sigma x. The question is, which is the ground state of this Hamiltonian? And it should be really simple because, as we can see, we can solve the problem, for example, for 1 and then tensorize for all the n qubits. So the question is, who is the ground state of this mixer? And the response is like the sum of all the possible bit strings that can be prepared with the Hadamard gate. So just to explain properly, each term is a sigma x gate, so it's like 0, 1, 1, 0. If I apply the Hadamard gate looks like this. Changing basis to the sigma x gate, we got the sigma z. So this operator becomes diagonal. Sorry. And here it's easy to choose which is the ground state, or 0 or 1. What we need then to do is just to rechange basis. So actually our ground state looks like, for example, if I take the sigma x operator and apply it to the plus state, it will remain itself. And if I apply sigma x, the minus state, it will go in minus time itself. So what I need to do is just to prepare the tensor product of this plus state on n qubits. So to do so, I just need to apply the Hadamard gate to each qubit, prepared in the 0 state. So here, to do so, to just apply the quantum circuit is already prepared as initial state in the 0 state. So we need just to apply the Hadamard gate. And to do so, we need just to go through every qubit and apply H. So this is the structure of the circuit. So we start with this circuit here, and then we just alternate layers of cost circuit and mixed circuit. That's the QAOA ansatz. So if we change problem, for example, if we take an unconstrained problem, what we'll have to change will be the cost circuit related to the problem function that we want to minimize. If we take, for example, instead of an unconstrained problem, a constrained problem, then we have to change the mixer that we want to use. So these are the first and the ground state we were about to start. So now this is the structure, for example, of one layer of our algorithm. We have that we start in the 0 state, then we prepare the ground state of the mixer Hamiltonian, and apply in the first layer the cost circuit with a free parameter gamma 0, and the mixer circuit with a free parameter beta 0. And then we measure each string. Once we measure each string for each iteration, we will have one cost function. So what we would need to do is just to each time measure the cost related to the state that we are preparing and optimize the parameter gamma and beta. So for example, in this specific case of the graph that I computed, the minimal, the max cut is 12 and the min cut is 0. And here we see minus 12 and 0 because we are trying to solve a variational quantum problem that is, instead of a max problem, has been posed as a min problem. So we have to just take the cost function and minus the cost function. So this is how the spectrum of the Hamiltonian looks like. So here we have on the x-axis the values, so the possible cuts that we can have on that graph, and on the y-axis we have the frequency of these possible costs, and we want to find here the -12 solution. So as we can see, there are many more solutions. Here is probably the random guess, as stated before by Franz. And we want to optimize with this QAOA algorithm to find this state here, this cost -12. So the thing is, like, as pointed out as before by you, this is an example of problem where we have many symmetries. So we will have not to look in an unconstrained space, but in a constrained space. We just can look at the interval 0 to pi. This is really simple to understand from the mixer point of view, for example, because the mixer operator looks like this. It's just a product of rotations. So for each rotation, if I rotate from 0 to pi, I just be back in the same state. This is not trivial for the gamma parameter, because there we got many different possible values that could be irrational, okay? So in this case, as we see, all the possible values are integer numbers. So there is a interval where if I rotate enough, I will be back. I will like span all the circle. So this is an example of problem where we have symmetry, and so we can just look for a solution for the first layer in the interval 0 to pi. So here I want to show you how it looks like the optimization landscape for the first layer. For other layers, of course, I can do this. So for the first layer, we have on the x-axis the gamma parameter, and on the beta one on the y-axis the beta one. And here we can see how the energy landscape or optimization landscape looks like. So as we can see, we got two holes, and here is where we want to go, or in this one or in this one. At the first layer, we want to minimize the cost function. So we expect that our optimizer, our classical optimizer, will get us here or here. The thing is, like as I told before, this beta parameter is periodic in 2 pi, but for this specific case, due to the symmetry of the problem, it's periodic in 0 pi. So we can even just restrict our search in the lower part of our landscape. So as we can see, it's really easy to optimize for this specific problem, the optimization landscape. But for other problems, this is not ensured. So if we take like constraint problems or like more random cost functions on more hard graphs, the landscape will look a little bit different and hard to solve. Yes? It's like you add every time one layer. There is for some problems a way to guess which is the best one, but then you optimize all the parameters together, not locally one per one. So the thing is, like, you can see the first layer, and here the optimization just for the first layer is local, but then adding the other terms, you have to optimize the whole 2 to the 2n space. So it's a little bit harder, the optimization, and nothing will ensure you to converge the ground state. That's why it's an heuristic solution. So if you just call the optimize function, we will obtain this value, minus 9.25, let's say. Yeah. Each one of you will have different graphs. So if for my specific case, I got this value for the 8H graph. And so optimizing, we got this value. And here we can see, for example, how this classical optimizer that I've used converge to the minimum of the landscape. So it starts, actually, for this specific case, we do a grid search. We start with a grid search, and then we choose the best point of this grid search and optimize from that point. But in principle, you can start, due to this landscape, it's really easy to optimize. So wherever you start, you will converge in to the minimum. But here we can see how the optimizer try to look around for the solution. And this is like, as I told before, we start with a grid search. So we start with a very good point, and then we optimize and obtain a better point here, using an optimizer that is called Qubit. And just to tell you, there are many types of different optimizers that can be used for QAOA on VQE in general, like the gradient based, so gradient descent or quantum natural gradients. But there are other techniques like classical optimizer that do like stochastic gradient methods. And this one is an example of a gradient-free method. So this type of classical optimizer, you don't use the gradient to converge to the ground state, but other type of algorithm to search for the best solution. And here, for example, we can plot how this QAOA performs. Yes? Actually, there are some papers that claim that it's better to use stochastic ones due to the noise. Actually, I don't really know what stochastic gradients to avoid the noise. But actually, I implemented some algorithm of this on real computers, the IBM ones. And the big problem is like when you introduce noise, you are completely destroying, depends on the strength of the noise, the landscape. So it becomes really hard to converge, and the number of iterations that you need to do to try to go through the minimum, it becomes so big that you can't actually simulate on a real quantum computer. So there are many problems due to the real noise. There are some optimizers that have been constructed exactly with the purpose of try to converge even when there is some quantum noise in the game. But it's a hard stuff that we can maybe discuss later. So the thing is, like, we can optimize for many layers, and this is how the cost function looks like in the optimization at each level. And we can see that at the first layer, the energy was minus 9.24, and then we start to go to minus 12. That was the best, the max cut solution that we are looking for. And this is how the approximation ratio looks like. So incrementing the depth, we are better and better approximating the max cut solution of our problem. So we can, in principle, use many layers to converge more and more. But the big problem is like the more layers, the more the depth of the circuit. So the big problem actually is like it's the noise in the quantum computers that don't permit us to simulate for high depth levels. So actually, this is just something that we can do on the classical computer right now, because if you try to implement it on a real quantum computer, actually, this approximation ratio will go down due to the noise, because the more depth, the more gates, the more noise. And here, for example, we can see how these parameters, gamma and beta, are optimized layer by layer. And there is there seems like there is like an interpolation. Like there is a function that gets us from the beta parameter, for example, from layer 1 to layer 6, and we can, in principle, think that we can find an interpolation that will get us the function of beta for each gate. And this is something that for MaxCut, for example, problems has been demonstrated, but for other type of problems is not necessarily true. But here the interesting thing is, like, if we look at the beta parameter, it goes from in this case it goes to the value, let's say 2 pi, and this is something that we can expect from the beta parameter, because we expect that at each layer the cost function will increase. In this case, particularly decrease, because we are solving the minimum problem. So we expect that at each layer we will be every time more near to the ground state of our problem. And the mixer gate, what it does is to apply some rotations to each gate. So we expect that the more we are near to the ground state, the less we have to rotate our system to describe the solution. So this is something that we could expect from the problem. Yeah, that's the main difference between QAOA and quantum annealing. The thing is, like, in quantum annealing, it's like there is some discussion about that. It's really QAOA could do better than quantum annealing, because we have this freedom of parameters that, like, could get to not exactly a time evolution, not a time-dependent evolution. So there are some studies that try to understand that there could be like adiabatic jumps that will, like, let you more easily to the ground state. So there are some studies about the transitions between the ground state to the excited state that could be avoided with this QAOA, but not with quantum annealing. Because with quantum annealing you have to slowly move, and here you look for the best parameters. So sometimes it's better than slowly move. So that's. But for this case, it's really you can see that there is a big analogy between the QAOA and the quantum annealing, because that's something that you will expect if you do like a time evolution, time-dependent evolution. Okay, so. Here we have think about the QAOA using the X mixer, but actually we can choose something else. For example, what will happen if I choose, instead of the sigma X, the sigma Y? So what the performances of this algorithm, I will change. And actually, if you think about it in the quantum annealing point of view, you will expect that nothing will change, because both are good candidates to do transitions from the first Hamiltonian to the second one. It's like if I just prepare properly the ground state of this Hamiltonian and interpolate between this one and the cost function, the quantum adiabatic theorem will assure me that I will go from one ground state to the other. So actually, I will expect that this type of mixer will work well. And in fact, actually, this is what happens. What we need to do now is like instead of in preparing the mixer with the Rx rotation, we'll prepare the mixer with the Ry rotations. So here the 4 goes for each qubit. We perform a Ry rotation with a free parameter. And the other thing that we need to be careful to prepare is the ground state of the Y mixer. So in this case, we should just use this relationship that tells us that HS Y S dagger H is equal to Z, and then we can just directly prepare the ground state of this state as H, the S H gate and S gate. This, I start from the 0 state, I apply these 2 gates, and I will prepare the ground state of the Y mixer. So it's really similar to the previous ground state. We just have the phase introduction with the S gate. So once we do that, we get mostly a real similar landscape. And if we try to solve it, this is how the approximation ratio looks like. So it's like exactly the same behavior and solution layer by layer. There is some variability due to the fact that we are sampling quantum states, but the optimization of the parameter is mostly the same. So one thing that we can think about it, because we are really using this quantum analogy with the quantum adiabatic theorem, is like, what if I start with from a state that is slightly different from the ground state? So what if I, as initial state, choose something that is not exactly the ground state, but as an overlap that is not trivial zero, let's say. So in this exercise, what I want you to do were like prepare, instead of the plus state for the X mixer, prepare this state here. So I prepared the 0 state, and for each qubit of our system, I rotate it by a parameter theta. The thing is, like, when this parameter theta is pi over 2, I am preparing exactly the ground state of the X mixer, so the plus state for each qubit. The question is, now if I compare the results that I obtained, for example, for layer 1, varying this theta parameter, so varying the overlap between the ground state of the mixer that I'm using, what will change? So to prepare this parametric initial state, I just need to apply with a fixed theta. In this case, will not be a parameter. The rotation for each qubit, and then what I need to do is to be able to compute this overlap. So how much is this overlap between the plus state, that is the ground state of the X mixer, and this psi 0 that I'm preparing with this circuit? So actually, this is just simply the 1 plus the sine of theta over 2 to the power of the number of qubits, because I got, this is like a product state of n qubits. So for each qubit, the overlap between Ry applied to 0 and plus is 1 plus sin theta over 2. So this is the function that gives me the overlap between the ground state of the X mixer and the state that I'm preparing as initial state. And here I just wanted to show how the optimization looks like. So if the overlap is 0, I get an approximation ratio that is lower if I start exactly from the ground state. So that's really, it's like a monotone function of the overlap with the ground state. And this is something really important. So what we really want to do usually in our QAOA algorithm is to choose a proper mixer and start from the ground state of the mixer that we are that we want to use. And this is something that, if you think about it in the quantum annealing point of view, that is based on the quantum adiabatic theorem, is like I want to avoid. The quantum annealing is the idea is I start from the ground state and I evolve so slowly that I remain every time in the ground state. So if I start in a superposition of the ground state and many excited state, if I move slowly, I will go in with some probability in the ground state, but with other probabilities even in the other excited states. And this is something that, in some sense, gives us this intuition about the quantum annealing and the QAOA. So this is the exercise that I want you to live with. Is like, if we think from the classical point of view, this problem has a symmetry. And this symmetry is like, I'm choosing to a partition of two elements. So I'm choosing a subset A and B. But I can just relabel everything, every 0 to be a 1 and every 1 to be a 0, and I expect the same cost function. So there is like this, if I flip all my bits string, I will obtain the same cost function. This is a symmetry that can be reflected also in the quantum case. So here, this symmetry is reflected here. If I get that C is sum over ij, wij, xi, 1 minus xj, I can write it even in this way, and it will look the same. So from the quantum point of view, as I said before, the idea is like if I flip my string, I will get the same cost. So what is the operator, quantum speaking, that does this flip? So for a single qubit, the flip is like I want to an operator h that applied to 0 gives me 1, and applied to 1 gives me 0. Who's the operator is sigma x. So this h is sigma x. In the case of n-bit string, this operator, let's call it mx, will look like the product of sigma x I. So like sigma x 0 times sigma x 1. Because if I take this operator and apply to a computational basis state, will map me in the bit flip version of my computational basis state. So what it means that we have this symmetry in our problem? That means that if I take this operator here, it commutes with my Hamiltonian. From the people from physics, this will be like clear, like what it means, like the symmetry is a commutation, is an operator that commutes with the Hamiltonian. So that means that aimx h minus is equal to 0. How can we see this from the operator, the Pauli operator point of view? Is h, as we stated before, is a sum of wij's, zi, zj. So let's take, for example, one term. If I take one term, mx is a product of sigma xi, and the term zi, zj looks like this. So we just need to, I will not go through the demonstration, but if mx commute with zi, zj for each I and j, also the sum will commute, because this operator is linear. So this is true. So we have that in the quantum case, this corresponds to this symmetry of the problem. The idea is like, can we use the symmetry like to reduce the dimension of the problem, and even maybe the depth of the circuit? So I will let you with this question maybe for some minutes, and then I will try to help you to understand if the idea is like we got this symmetry of the problem. Can we reduce the dimension of the problem using this?
Well, a big thank you to the both of you.